Welcome to the Ultimate Whiteboard Challenge crash course for AWS Python Data Engineering interviews. Over the next session, you're going to walk through 20 real-world coding and system design challenges, not just puzzle-style brain teasers, but the exact kind of problems that come up in top-tier tech companies. Each challenge is structured to make you interview-ready. We'll start with algorithm warm-ups that test your thinking in Big O notation. Then, we move into data structure mastery with hash maps, heaps, and sliding windows. From there, we scale up to real AWS-powered scenarios involving ETL, step functions, S3, and DynamoDB. And finally, we'll finish with the curveball system design problems that senior interviewers love. For every challenge, here's what you'll get. A clear problem statement with time limits, just like in a real interview. Production-level Python walkthroughs with error handling and testing. Follow-up questions that simulate real interview stress tests and curveballs. AWS well-architected insights woven into each answer, focusing on scalability, cost, and reliability. A final practice challenge for you, so you don't just watch, you actively sharpen your skills. By the end of this, you won't just know how to code, you'll know how to communicate, architect, and impress like a data engineer who is ready to own the whiteboard. So grab a notepad and treat this like a mock interview. If you stick with me through all 20 challenges, you will know exactly how to crush these problems when they come up. Ready? Let's dive in. Transition to Level 1, Warm-up Stage. We begin with Level 1, Algorithm Warm-ups. These challenges sharpen your thinking, test Big O awareness, and get you moving fast under pressure. Whiteboard Challenge 1, Detect anagrams with Python like a pro. Question: what is this challenge and why does it matter? Answer: let's start with an algorithm warm-up that looks deceptively simple but carries deep interview value. Detecting anagrams is a classic because it forces you to weigh trade-offs between different solutions, the straightforward sorting-based approach, Big O of n log n, versus the more optimal hash map-based approach, Big O of n. Interviewers love it because it tests whether you instinctively reach for the obvious solution or pause to think about performance. Beyond interviews, this logic maps directly to real-world data engineering problems like deduplication, record linkage, grouping, and quality checks in ETL pipelines. Handling this problem cleanly, with input validation and normalization, shows not just algorithmic skill but also production-minded engineering discipline. The task: write a Python function that returns true if two strings are anagrams, false otherwise. Sorting is not allowed because it's Big O of n log n. The goal is Big O of n using a hash map. But remember, in a real interview, you're also judged on handling messy inputs, so think beyond a happy path. The challenge and time box. You have 7 to 10 minutes. Write clean, production-ready code, input validation, efficiency, and simple tests. Walk the interviewer through your thought process, start with quick rejections, then move into hash map logic. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We import defaultdict for counting character frequencies. Counter is later used for the Pythonic one-liner. The string module reminds us of Python's text utilities, though here we rely mainly on .isalpha parentheses. We validate inputs early, raising an error if either argument isn't a string. This shows production-minded robustness, not just solving the toy problem. The normalize parentheses helper cleans input, it lowercase characters and removes anything that isn't a letter. This ensures messy real-world strings are handled correctly. We apply normalization to both inputs so comparisons are fair regardless of casing or punctuation. If the clean strings are different lengths, they cannot be anagrams. This is a fast Big O of 1 rejection step. We build a frequency map from the first string, each character count is increment in a defaultdict. We walk through the second string, decrementing counts. If a character doesn't exist or drops below 0, the strings are not anagrams. At the end, all counts must return to 0. If they do, the strings are true anagrams. We run sample test cases to validate correctness, lowercase, case-insensitive, punctuation handling, and negative cases. As a bonus, we demonstrate a Pythonic one-liner using counter. It's concise and expressive, but the hash map approach is more interview-friendly. Follow-up questions. Follow-up question 1. What is the time and space complexity of your solution, and why is it superior to a sorting-based approach? Answer. The time complexity is big O of n, where n is the length of the strings, because we iterate through each string just once. The space complexity is big O of k, where k is the number of unique characters. For a fixed character set like ASCII, this is considered big O of 1 constant space. This is significantly better than the sorting approach. Sorted of S1 is equal to sorted of S2, which has a time complexity of big O of n log n due to the sort. Follow-up question 2, how would you modify this to handle case insensitivity, spaces, or even punctuation? Answer, that's where normalization comes in. In our solution, we already introduced a normalize parentheses helper, which lowercase characters and removes non-alphabetic symbols. But you could extend it further depending on the requirements. For example, if spaces and punctuation should be ignored but digits matter, you'd filter differently. If you're working with multilingual data, you'd use Python's Unicode data library to normalize characters, for example, turn resume into resume. The key point in an interview is to show that you don't just compare raw strings, you think critically about how real-world input is messy and needs to be cleaned before comparison. That shows maturity beyond the textbook algorithm. Follow-up question 3, curveball. What if the strings only contained lowercase English letters A to Z and you were on a system with very limited memory, making a hash map undesirable? Answer, that's a great constraint. I would switch from a hash map to a fixed-size array of 26 integers, representing the counts 4 through Z. I would use the character's ASCII value, the ord of the character minus the ord of A, to find its index in the array. This approach maintains the big O of n time complexity but reduces the space complexity to a true big O of 1, as the array's size is constant regardless of the input string's length. How to ace this whiteboard challenge? How to explain it? Start by briefly mentioning the less optimal sorting solution, big O of n log n, to show you have considered multiple approaches. Then, introduce your hash map solution as the more efficient method. Walk through the logic, build the frequency map, then check and deconstruct it with the second string. Why it impresses, this solution screams efficiency-first thinking. It is clean, readable, and handles edge cases properly. By explaining the time and space complexity trade-offs, you are not just coding, you are demonstrating a deep understanding of computer science fundamentals. AWS well-architected connection, this directly relates to the performance efficiency pillar. Even on a micro level, you are choosing an architecture, a data structure, that uses compute resources, CPU time, more efficiently. This mindset is critical when designing large-scale AWS data pipelines where every bit of performance matters. Here's a challenge for you to practice and take your skills to the next level for interviews. Adapt the function for multilingual strings, for example, Unicode characters. For example, how would you handle accented letters like resume? A naive comparison might say resume and resume are different, even though a human considers them the same. To solve this, you need to think about Unicode normalization, using Python's Unicode data.normalize with NFC or NFD forms to standardize characters. This forces you to confront globalization concerns. Does your algorithm work only for English, or is it robust enough for international datasets? In an AWS scale data pipeline, where inputs may come from many languages, this kind of design consideration is critical. Whiteboard Challenge 2, Mastering SQL Window Functions for Ranking. Question: what is this challenge and why does it matter? Answer: this is a quintessential data engineering SQL challenge. Interviewers use it to see if you can move beyond basic group by clauses and use modern, powerful SQL features. Window functions are the bedrock of analytics, used for everything from creating leaderboards and segmenting customers to calculating time series trends. Acing this proves you can write efficient, readable, and complex queries required for any serious data transformation or business intelligence task. Failing this is often a major red flag. The challenge and time box. You have 5 to 7 minutes. Given a table of sales data, write a single SQL query to find the top 3 best-selling products within each product category. The key is to demonstrate mastery of window functions and use common table expressions, CTEs, for clarity. Here is the SQL implementation I would use. Disclaimer: always test code in a non-production environment. We start by defining a CTE sales underscore data with sample rows. In an interview, this makes the query runnable without needing external tables. It also demonstrates you know how to use CTEs not just for logic structuring but also for test data setup. First, we create a CTE called product sales. Before we can rank products, we need to know their total sales. This step aggregates the raw data, calculating the sum of sale underscore amount for each unique combination of category and product. This is the core of the solution. We use the row underscore number parentheses window function. Partition by category tells the function to reset the counter for each new category. It is like a temporary group by for the window function. Order by total underscore sales desk sorts the products within that partition, so the best-selling one gets rank 1. Finally, we can treat the calculated rank underscore number as a regular column. We select from our rank sales CTE and simply filter for all rows where the rank is less than or equal to 3. This cleanly gives us our desired result. This is what the query output would look like. It clearly shows the top 3 products per category ranked by sales. Presenting results helps interviewers visualize correctness quickly. Modern warehouses, Snowflake, BigQuery, Redshift partially, allow the qualify clause, which lets you filter directly on window function results without wrapping them in CTEs. It's cleaner, but less portable across all SQL engines. Mentioning this shows you know cutting-edge SQL features. Follow-up questions. Follow-up question 1. What is the difference between row underscore number parentheses, rank parentheses, and dense underscore rank parentheses? Answer: this is the most common follow-up. Row underscore number parentheses gives a unique, sequential number to each row in the partition. If there's a tie in sales, it assigns different ranks arbitrarily. Rank parentheses gives tied rows the same rank but then skips the next ranks. For example, 2 products tied for second place would both get rank 2, and the next product would get rank 4. Dense underscore rank parentheses also gives tied rows the same rank, but it does not skip ranks. The next product would get rank 3. For a top-end list, row underscore number is often safest, but for scenarios where you must include all ties, you would use rank or dense underscore rank. Follow-up question 2, your query is great for readability. But could you write it without using multiple CTEs? Answer: absolutely. You can nest the queries using subqueries. You would place the product sales aggregation query in the from clause of the ranking query, and then wrap that entire result in another subquery to perform the final where rank underscore number is less than or equal to 3 filter. While it is functionally identical, using CTEs with names like product sales and rank sales makes the logic much easier to follow, debug, and maintain, which is a critical practice in professional data engineering. Follow-up question 3, curveball: how would this query perform on a massive, billion-row table in Amazon Redshift, and how could you optimize the underlying table structure for it? Answer: on a massive table, the performance would depend heavily on Redshift's data distribution and sort keys. The partition by category clause would trigger a significant data shuffle if the data is not distributed correctly. To optimize, I would set the table's dist key to category. This CO locates all data for the same category on the same node, making the partitioning step extremely fast by avoiding network traffic. Additionally, I would set a compound sort key on category, total underscore sales, to pre-sort the data, which would make the order by operation within the window function incredibly efficient. For even faster access, You could pre-aggregate data into a materialized view or use spectrum/parquet partitioning in S3 if querying via Athena. How to ace this whiteboard challenge? How to explain it? Start by declaring your intent to use CTEs for readability. Explain the logic in stages: first aggregate, then rank, then filter. When you write the window function, verbally break down the partition by and order by clauses to show you understand exactly how they work. Why it impresses: using CTEs demonstrates clean, modern SQL, proactively mentioning the difference between row_number, rank, and dense_rank before the interviewer asks shows deep knowledge. Connecting the query to the underlying data architecture, like in the Redshift question, elevates you from a SQL writer to a data engineer who thinks about performance at scale. AWS well-architected connection: this directly relates to the performance efficiency and cost optimization pillars. An efficient query with window functions is faster and cheaper to run on services like Athena and Redshift than an old-fashioned, multi-step process with complex joins. Understanding how dist key and sort key optimize this specific query shows you can design performant and cost-effective data models on AWS. Here's a challenge for you to practice and take your skills to the next level for interviews. Using the same sales_data, write a SQL query to calculate the month-over-month sales growth percentage for each product category. Hint: this requires another window function, lag parentheses, which allows you to access data from a previous row in your partition. You will need to partition by category and order by month.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or both to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 3. Flatten nested JSON with Python like a data pro. Question: what is this challenge and why does it matter? Answer: this is one of the most common, real-world tasks for a data engineer. Data from APIs, IoT devices, and clickstream logs almost always arrives as nested JSON. However, data warehouses and analytics engines like Redshift, Athena, and Spark are optimized for flat, tabular structures. This challenge tests your ability to perform this critical ETL step. Interviewers want to see if you instinctively reach for powerful, industry-standard tools like pandas, and if you can reason through the underlying logic for when those tools aren't available. Acing this demonstrates practical, hands-on experience in preparing raw data for analytics. The challenge and time box. You have 10 to 15 minutes. Given a list of nested JSON objects representing clickstream data, write Python code to flatten it into a tabular format. Prioritize the idiomatic pandas solution, but be prepared to explain and implement a vanilla Python alternative to show your algorithmic depth. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We start with a realistic data sample, a Python list where each element is a nested dictionary representing a user session. This structure is common for log files and API responses. First, we demonstrate the best practice solution using pandas.json_normalize. This is the tool data professionals use because it is fast, memory efficient, and concise. Record_path sadface purchases is the key. It tells pandas to create a new row for each item in the purchases list. Meta specifies which parent-level fields should be duplicated for each new row. Errors equals ignore prevents crashes if a key is missing. Next, we show how to solve the problem without pandas. This demonstrates a deeper understanding of the logic that libraries often abstract away. We loop through each session and create a parent_info dictionary. We use .get to safely extract top-level and nested user details, which prevents errors if keys are missing from a record. Inside the main loop, we iterate through the nested purchases list. For each purchase, we create a new flat_record by copying the parent data and updating it with the purchase details, then append it to our final list. The output of our vanilla function is a list of flat dictionaries. This is a standard, clean format that can be easily loaded into a pandas data frame, proving our logic is sound and produces a usable, tabular result. Follow-up questions. Follow-up question 1. What are the trade-offs between your two solutions? Answer: the pandas JSON_normalize solution is superior for production code. It is highly optimized, written in C, less verbose, and handles edge cases like missing keys automatically. The vanilla Python solution is more transparent and flexible, showing the underlying logic. It is useful in environments without pandas, like a lightweight AWS Lambda, but is more error-prone and significantly slower for large datasets. You use the vanilla approach to prove you understand the algorithm, but you use the pandas approach to get the job done efficiently. Follow-up question 2. How would you scale this for millions of JSON files, terabytes of data, in S3? Answer: for that scale, both in-memory Python solutions will fail. The correct approach is to use a distributed processing engine like AWS Glue or Spark. You would use spark.read.json, s3/path/data/, which can read and parse the JSON in parallel across a cluster. Then, you would use Spark's data frame transformations, specifically the explode function on the purchases column, to achieve the same tabular result. This distributes the memory and compute load, allowing it to scale almost infinitely. The final, flattened data would then be written to S3 in a columnar format like Parquet for efficient querying by Athena or Redshift. Follow-up question 3, curveball: what if the JSON schema changes frequently, with new fields being added by producers? Answer: this is a classic data engineering problem called schema evolution. A rigid script would fail. The robust solution is to design a pipeline that can handle these changes. On AWS, you would use AWS Glue Schema Registry. It allows producers to register new schema versions, and consumers, like Glue ETL jobs or Kinesis applications, can be configured to either reject non-conforming records or, more powerfully, adapt to the new schema automatically. This moves the logic from brittle, hard-coded scripts to a managed, governable process, which is essential for maintaining data quality in production. How to ace this whiteboard challenge? How to explain it? Start with the pandas solution, calling it the production standard. Explain record_path and meta clearly. Then, offer to write the vanilla Python version to demonstrate you understand the core logic of exploding and joining. Why it impresses: this two-pronged approach shows both pragmatism, using the right tool, and deep fundamentals. Bringing up the scaling limitations and pivoting to a Spark/Glue solution shows you think like a senior data engineer, not just a Python coder. AWS well-architected connection: this directly ties to the performance efficiency pillar. You are choosing the right tool for the job size, pandas for in-memory tasks and AWS Glue/Spark for distributed, large-scale processing. Discussing schema evolution also touches on operational excellence, as it is about building robust, maintainable pipelines. Here's a challenge for you to practice and take your skills to the next level for interviews. Adapt your function to handle a JSON structure where there are multiple levels of lists to explode. For example, what if each purchase item could also have a list of tags? Item_ID, item_a, price, 100, tags, sale, electronics. How would you produce a final table where there is one row per tag? /n/n hint: this can be done by chaining JSON_normalize or by using the explode function method in pandas multiple times. Whiteboard challenge 4, building a bulletproof AWS S3 pagination utility. Question: what is this challenge and why does it matter? Answer: this is a fundamental, real-world task for any data engineer on AWS. The list_objects_v2 API returns a maximum of 1,000 objects per call to prevent overload. In data pipelines where buckets contain millions of files, failing to handle this pagination correctly means you will silently miss most of your data, leading to incomplete ETL jobs and corrupted analytics. This challenge tests your direct experience with the AWS SDK, Bodo 3, and your ability to write robust code that works at scale. It is a major red flag if a candidate cannot solve this. The challenge and time box. You have 10 to 12 minutes. Write a Python function that retrieves all object keys from a given S3 bucket and prefix. First, build a version that correctly handles the API's pagination. Then, discuss how you would optimize it for memory when dealing with millions of objects. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We start the manual function by initializing the Bodo 3 client, an empty list to hold the keys, and a dictionary quarks to manage the API parameters. We start an infinite while loop that will continuously make API calls until we explicitly break out of it. Inside the loop, we make the call to list_objects_v2, passing our parameters dictionary. This will fetch one page of up to 1,000 objects. We safely check if the contents key exists in the response, then loop through the returned objects and append each object's key to our master list. This is the crucial exit condition. If the truncated flag in the response is false, it means we have reached the last page of results, and we break the loop. If the loop continues, we grab the next continuation token from the response and add it to our quarks dictionary. The next API call will use this token to fetch the next page. In our improved generator function, we use Boto3's built-in paginator. We get the paginator for the list_objects_v2 operation and call .paginate parentheses to create an iterator that handles the API calls for us. Finally, we loop through the pages provided by the paginator. For each object within a page, we yield its key. This turns the function into a memory-efficient generator, streaming keys one by one. We define an example usage block that runs only when the script is executed directly. Inside, we set placeholder values for a bucket and prefix to demonstrate how the functions would be called. This section demonstrates how to use the list_all_s3_keys function. It would call the function, store the entire list of keys in memory, and then print the total count. This demonstrates the more efficient generator pattern. We loop through the results of stream_s3_keys, processing each key one by one. This approach is ideal for large datasets as it keeps memory usage low. Follow-up questions. Follow-up question 1. Your first solution collects all keys in a list. What is the risk of this approach in a real-world scenario? Answer. The primary risk is memory exhaustion. If a bucket prefix contains millions or billions of object keys, storing them all in a list could consume gigabytes of RAM, crashing the application. This is especially dangerous in memory-constrained environments like AWS Lambda or small EC2 instances. The generator-based approach, Yield, avoids this entirely by maintaining a tiny, constant memory footprint. Follow-up question 2, you showed the Boto3 paginator. Why is it generally preferred over the manual while loop implementation? Answer, the paginator is preferred for 3 reasons: robustness, simplicity, and maintainability. It abstracts away the complex logic of token management and stopping conditions, reducing the chance of bugs. It also automatically handles some retry logic under the hood. The code is much cleaner and more declarative, making it easier for other engineers to read and maintain. Follow-up question 3. Curveball: the list_objects_v2 API can be slow and costly if you run it frequently on a bucket with billions of objects. What is a better architectural pattern for this scale? Answer, that's a great architectural question. At that scale, API listing is inefficient. The superior pattern is to use Amazon S3 inventory. You can configure S3 to generate a daily or weekly report that lists every single object along with its metadata. This report is delivered as a set of CSV, ORC, or PAR-K files to another S3 location. Our data pipeline can then process this manifest file directly, which is far more scalable, faster, and cheaper than making billions of API calls. How to ace this whiteboard challenge? How to explain it? Start by clearly explaining the 1000 object limit of the S3 API, present the manual while loop solution first, as it proves you understand the underlying pagination mechanism, continuation token. Then, proactively introduce the generator/paginator solution as the memory-efficient, production-grade improvement. Why it impresses, many candidates simply forget about pagination. By handling it correctly, you show production readiness. By discussing the memory trade-offs, list versus generator, and the architectural alternative, S3 inventory, you elevate yourself from someone who just writes code to an engineer who designs scalable systems. AWS well-architected connection, this directly hits the reliability pillar, by not losing data, performance efficiency, by using memory-efficient generators, and cost optimization, by suggesting S3 inventory at scale to reduce API costs. Here's a challenge for you to practice and take your skills to the next level for interviews. Adapt the stream_s3_keys generator function to accept an optional min_last_modified argument, a Python datetime object. The function should only yield keys for objects that were modified after this timestamp. This requires you to inspect the last modified attribute within the object's metadata and perform a timezone-aware comparison. This simulates a very common incremental data processing pattern.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the Answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or both to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Transition to Level 2, Intermediate. We've warmed up with Python algorithms and SQL fundamentals. You've proven you can handle the basics under time pressure. Now, we step into the intermediate zone, where data handling, transformations, and AWS awareness start coming into play. Whiteboard Challenge 5, Deduplicating Data in an S3 Data Lake. Question: what is this challenge and why does it matter? Answer: this is a critical, real-world data quality problem. Ingestion pipelines often receive duplicate data, either as identical files or as overlapping records within files. If not handled, these duplicates corrupt analytics, skew ML models, and inflate storage costs. This challenge tests if a candidate can design a robust deduplication strategy using the right tools, from scalable Spark jobs for record-level cleansing to efficient file-level checks. Acing this proves you can build trustworthy, production-grade data pipelines. The challenge and time box. You have 12 to 15 minutes. An S3 location receives daily batch files, for example, JSON. Design a solution to remove duplicate records. First, show the primary method using PySpark to handle record-level duplicates. Then, discuss how you could optimize the process by identifying and filtering out identical files before they are even processed. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. Inside our function, we start by reading all the JSON files from the specified S3 input path into a Spark data frame. Spark's distributed nature handles reading many files in parallel efficiently. We perform an initial count of the rows. This is a good practice for logging and monitoring, as it allows us to quantify how many duplicates were removed. This is the core of the solution. We use Spark's drop duplicates parentheses method. By specifying a subset of columns like user_ID and event_time, we define our business key for uniqueness. Spark handles the complex distributed shuffle required to find and remove these duplicates across all nodes. After deduplication, we count the records again to see the result. The difference between initial _count and final _count is the number of duplicates removed. Finally, we write the clean data frame back to S3. We use the PAR-K format because it is columnar and highly optimized for fast analytical queries in downstream systems like Athena or Redshift. We start our example usage block with the standard if __name _ is equal to __main__, check. This ensures the code inside only runs when the script is executed directly. Inside the block, we initialize a Spark session. This is standard boilerplate for any Spark application, whether it is running on AWS Glue, EMR, or locally. We define our input and output S3 paths as variables. This makes the job configuration clear and easy to modify or parameterize in a production workflow. Finally, we call our main run_deduplication_job function, passing in the active Spark session and the configured paths to execute the ETL process. Follow-up questions. Follow-up question 1. Your Spark job is great for record-level issues, but what if the source sends 10 1 GB files that are bit-for-bit identical? Your job would still read all 10 GB. How can you prevent this? Answer: that's a perfect use case for a file-level deduplication preprocessing step. Before launching the Spark job, a lightweight Python script could scan the S3 prefix. It would calculate a content hash, like MD5 or SHA-256, for each file. The most efficient way to do this without downloading the file is often by using S3's etag metadata, which for single-part uploads is the file's MD5 hash. By comparing etags, we can identify identical files, keep one, and either delete or move the others to an archive location before the expensive Spark job even starts. This saves significant processing cost and time. Follow-up question 2, is drop duplicates parentheses always the most efficient method in Spark? What are its performance implications? Answer: no, it is not always the most efficient. Drop duplicates parentheses requires a full shuffle, where Spark repartitions the entire dataset across the cluster based on the key columns. This is very network and I/O intensive. For massive datasets, a more performant approach is to use a window function like row_number parentheses. You would do row_number parentheses over, partition by user_ID, event_time order by ingestion_timestamp desk. Then you filter for rows where the number is 1. This can be more efficient, especially if the data is already partitioned or sorted in a favorable way. Follow-up question 3. Curveball: you are deduplicating today's data, partition 2023-11-21. What if a late arriving record for today's date arrives in tomorrow's batch? How do you handle this cross-partition duplication? Answer: this is a classic late arriving data problem. The simple drop duplicates parentheses on a single partition will not work. The robust solution is to use a transactional data lake table format like Apache Iceberg, Hoodie, or Delta Lake. These formats support merge into, or upsert, operations. The daily Spark job would read the new batch of data and merge it into the main table, using the business key, user_ID, event_time, to match records. This allows the job to insert new records and update or ignore duplicates that already exist in the table, regardless of which daily partition they originally landed in. How to ace this whiteboard challenge? How to explain it? Start with the most common and scalable solution, record-level deduplication using Spark drop duplicates parentheses. Then, introduce file-level hashing or e-tag checks as a cost and performance optimization. This shows you can think in layers. Why it impresses? A basic answer just shows drop duplicates parentheses. A great answer discusses the performance cost, shuffles, compares it to window functions, and brings in architectural patterns like pre-filtering files and using transactional table formats like Hoodie or Iceberg for late arriving data. This demonstrates senior-level, end-to-end thinking. AWS well-architected connection. This directly relates to the reliability pillar, ensuring data integrity and trustworthiness, and cost optimization, by using file-level checks to avoid processing redundant data and choosing efficient Spark operations. Here's a challenge for you to practice and take your skills to the next level for interviews. Using Spark SQL, rewrite the record-level deduplication logic using the row_number parentheses window function. Your function should partition by user_ID and keep only the record with the most recent ingestion_TS for each user. This is a common pattern for keeping the latest version of a record. Whiteboard Challenge 6. Solving the small files problem in an S3 data lake. Question: what is this challenge and why does it matter? Answer: that a small files problem is a notorious performance killer in cloud data lakes. When ingestion pipelines dump millions of tiny files into S3, query engines like Athena and Spark suffer from massive overhead. They have to list, open, and read metadata for thousands of files just to answer a simple query, leading to high latency and skyrocketing costs. Solving this demonstrates a candidate's understanding of how distributed systems work and their ability to design critical data optimization pipelines for performance and cost efficiency. The challenge and time box. You have 12 to 15 minutes. Design a Spark job that consolidates thousands of small JSON files from an S3 path into a smaller number of larger, query-optimized Parquet files. Your solution should also repartition the data by a key like event_date for query pruning. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. First, we read all the small JSON files under a given prefix into a single Spark data frame. Spark's engine is designed to handle this parallel read operation efficiently. This is a key step for compaction. We use coalesce, 16, to reduce the number of in-memory partitions to 16. This is generally more efficient than repartition when you are only decreasing partitions, as it avoids a full data shuffle. This is the right stage where two optimizations occur. We write in Parquet format for columnar benefits, and we use .partition by event_date. This tells Spark to create a Hive-style partition structure on disk, for example, /event_date equals 2023-11-22/, which is critical for query performance. We start our example execution block, which is standard practice for making Python scripts runnable. We initialize our Spark session, giving our application a descriptive name that will appear in the Spark UI for monitoring. We define the input and output S3 paths. The job is designed to read a general path and let the partition by command create the specific date-based subdirectories in the output location. Finally, we call our main function with the Spark session and paths to execute the job. Follow-up questions. Follow-up question 1. Why is Parquet so much better than JSON for analytics? Answer: Parquet is a columnar storage format. This means if your query is select user_ID, city from events, the engine only reads the data for the user_ID and city columns. JSON is row-oriented, so the engine would have to read the entire row, every field, for every record, which is much slower. Additionally, Parquet has superior compression and encoding schemes, drastically reducing storage size and I/O, which lowers query costs in services like Athena. Follow-up question 2, how do you determine the optimal file size, and what's the difference between repartition parentheses and coalesce parentheses? Answer, the ideal file size for S3-based query engines is between 128 megabytes and 1 gigabyte. To achieve this, you would calculate the total size of your input data and divide by your target size to find the right number of partitions. Repartition parentheses triggers a full shuffle and can increase or decrease partitions, but it is expensive. Coalesce parentheses is a cheaper optimization that only decreases partitions by merging them on existing nodes, avoiding a full shuffle. For pure compaction, coalesce is usually the better choice. Follow-up question 3, curveball, your job runs on a schedule. What if your pipeline ingests small files continuously? How would you prevent the problem from happening in the first place? Answer, this requires designing the ingestion pipeline correctly. Instead of a downstream batch fix, you would solve it at the source. The best AWS native tool for this is Kinesis Data Firehose. You can configure a delivery stream with buffering hints, telling it to batch incoming records until it reaches a certain size, for example, 128 megabytes, or a certain time has passed, for example, 15 minutes, before writing a single, larger file to S3. This proactive buffering is far more efficient than constantly running compaction jobs. How to ace this whiteboard challenge? How to explain it? Clearly define the small files problem, metadata overhead. Present compaction into Parquet with partitioning as the two-part solution. Explain the why for each, Parquet for columnar reads, partitioning for query pruning. Why it impresses, a great answer goes beyond the code. Mentioning the ideal file size range, 128 megabytes to 1 gigabyte, explaining coalesce versus repartition, and suggesting proactive solutions like Kinesis Firehose buffering shows you have deep, practical experience. AWS well-architected connection. This is a textbook example of the performance efficiency and cost optimization pillars. Optimizing file layout and format directly reduces query latency and the amount of data scanned, which lowers costs in Athena, Redshift Spectrum, and EMR. Here's a challenge for you to practice and take your skills to the next level for interviews. Extend the compaction logic to write the data not only partitioned by event_date but also bucket by user_ID into 16 buckets, bucket by 16 user_ID. Then, explain how this bucketing would significantly improve the performance of a join operation in Spark when joining this events table with a large customer table on user_ID.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this, you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or both to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, Dynamo, DB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python data engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 7, Handling Late Arriving Data in AWS Pipelines. Question: what is this challenge and why does it matter? Answer: late arriving data is an unavoidable, real-world problem. Imagine a user event happens at 11:59 p.m. but is ingested at 12:05 a.m. due to network lag. A naive daily job will misplace this event in the wrong day's partition, corrupting all downstream analytics. Handling this correctly is critical for data accuracy and trust. This challenge tests if you can design pipelines that balance accuracy, latency, and cost, the core trade-off in data engineering. The challenge and time box. You have 12 to 15 minutes. Design a data pipeline that processes events and correctly handles records that arrive late. First, show the fundamental approach for a daily batch job. Then, show the more advanced equivalent for a real-time streaming pipeline using Spark. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. In our batch solution, this is the most critical step. We create an event_date column based on the event's own timestamp. This decouples the data's location from the job's execution time. We then write the data using partition by event_date. A late event from yesterday will automatically be placed in yesterday's folder. Mode, append, ensures we do not overwrite existing data in that partition. For our streaming solution, we start by setting up a read stream from a source like Kinesis. Spark will continuously ingest new records as they arrive. This is the core of the streaming logic. With watermark, event_timestamp, 1 hour, tells Spark to keep state for aggregation windows, in this case, daily windows, for an extra hour, allowing late events to be included in the correct day's count. Finally, we write the results of our streaming aggregation to S3. The checkpoint location is critical for fault tolerance, allowing the stream to restart exactly where it left off. Follow-up questions. Follow-up question 1. Your batch solution appends data, potentially creating duplicates. How do downstream consumers get an accurate daily count? Answer: this is a key trade-off of the simple append strategy. The data in the lake is, eventually, consistent. Any downstream query that needs a correct daily count must first perform a read-time deduplication. For example, a query would read the entire event_date equals 2023-11-21 partition and then apply df.drop duplicates, event_id, before calculating any aggregates. The responsibility for correctness is shifted to the reader. Follow-up question 2. what's the trade-off in setting the streaming watermark duration? What if it is too short or too long? Answer: a short watermark, for example, 5 minutes, results in low latency aggregations and uses less memory/state, but you risk dropping more late data. A long watermark, for example, 24 hours, ensures higher accuracy by capturing very late data, but it significantly increases the amount of state Spark must maintain, which increases memory requirements, recovery time, and the latency of final results. The right duration is always a business decision balancing accuracy versus freshness and cost. Follow-up question 3. Curveball: what if you cannot afford read-time deduplication for your batch pipeline and need the data to be clean at rest? Answer: for that, you need to evolve beyond a simple Parquet data lake and use a transactional table format like Apache Hudi, Apache Iceberg, or Delta Lake. These formats provide merge into, upsert, capabilities. Instead of just appending, your daily batch job would merge the new data into the target table. This process can atomically insert new records and update or ignore records that already exist based on a primary key. This keeps the data clean at rest and is far more efficient for query engines. How to ace this whiteboard challenge? How to explain it: start with a story. An event occurs at 11:59 p.m. but arrives at 12:05 a.m. We must put it in yesterday's data. Present the batch solution, partition by event time, first as the foundation. Then, introduce streaming with watermarking as the real-time equivalent. Why it impresses: a great answer covers both batch and streaming paradigms. You demonstrate senior-level thinking when you discuss the downstream consequences, read-time dedup, and then proactively propose superior architectures like Hudi/Iceberg that solve those consequences. AWS well-architected connection: this directly addresses the reliability pillar. A pipeline that correctly handles late data is fundamentally more reliable and produces trustworthy data. Discussing transactional formats also touches on performance efficiency by improving query performance for end users. Here's a challenge for you to practice and take your skills to the next level for interviews. Design and pseudocode a backfill/reconciliation job. This job runs once a day. It should identify all data partitions from the last 3 days that have received new data, that is, their file modification times have changed. For each of these dirty partitions, it should trigger a downstream aggregation job to recalculate and update the daily summary reports. Whiteboard Challenge 8, Implementing data quality checks before a Redshift load. Question: what is this challenge and why does it matter? Answer: data engineers are the guardians of data quality. If data with nulls, duplicates, or incorrect volumes is loaded into a data warehouse like Redshift, all downstream dashboards and ML models become untrustworthy. This garbage in, garbage out problem erodes trust in the data platform. This challenge tests if you can design a validation gate to programmatically check data before it is loaded, ensuring the reliability and integrity of the entire analytics ecosystem. The challenge and time box. You have 12 to 15 minutes. Data is staged in S3 and is queryable via Athena. Write a single, modular SQL query that performs several data quality checks on a staging table, including nulls and key columns and duplicate primary keys. The query should return a single count of all failing records. A result of 0 means the data is clean. Here is the SQL implementation I would use. Disclaimer: always test code in a non-production environment. We start with a common table expression, CTE, to simulate our staging data. This makes the query self-contained and demonstrates the types of bad data we are looking for: a record with a null user_ID and another with a duplicate event_ID. Our first modular check is 4 null values in critical columns. This CTE scans the staging data and returns any record where user_ID is null, along with a descriptive error message. Our second check finds duplicate primary keys. We first perform a group by in a subquery to count occurrences of each event_ID, and then the outer query filters for any IDs that appear more than once. This CTE aggregates all our individual checks into a single result set. Using union all is an efficient way to stack the results from different validation rules. The final select is designed for automation. It returns a single integer, the total count of failed records. An orchestration tool can easily consume this result to decide whether to proceed with the pipeline or halt it. Follow-up questions. Follow-up question 1. How would you integrate this SQL check into an automated AWS pipeline, for example, using step functions? Answer. This SQL query is perfect for automation. In a step function, I would have a state that calls the Athena Start Query Execution API. The next state would poll for completion using getQuery execution. Once complete, a getQuery results call would fetch the single count of total failing records. This result would then feed into a choice state, which acts as a conditional branch. If the count is 0, it proceeds to the load to Redshift state. If the count is greater than 0, it transitions to a send failure alert state using SNS. Follow-up question 2. Custom SQL is good for a few checks. When and why would you graduate to a dedicated data quality framework like Great Expectations or DQ? Answer. You would graduate when you need more complex, declarative, and scalable checks. Great Expectations is a Python framework that lets you define a suite of expectations in a human-readable format, for example, expect column mean to be between x and y. It is great for Airflow integration and automatically generates data documentation. DQ is a Scala/Spark library from AWS, ideal for running validation directly within a glue job on terabyte-scale data. It is the go-to for large-scale validation inside your Spark ETL process. Follow-up question 3. Curveball: a check fails, and your pipeline stops, meaning the business gets no data for the day. What's a more resilient production pattern than a hard failure? Answer. A hard failure is risky. A more resilient pattern is to quarantine bad data. Instead of just counting errors, the validation job would split the data into two streams. The good records that pass all checks are written to an approved/S3 prefix and loaded into Redshift as planned. The bad records are written to a quarantine/prefix, along with metadata about why they failed. The pipeline itself succeeds, but it sends an alert to the data team to investigate the quarantined records. This ensures the business gets the majority of clean data without delay while isolating issues for later analysis. How to ace this whiteboard challenge? How to explain it? Start by explaining the gatekeeper principle. Write the modular SQL using CTEs, showing how each check is a self-contained unit. The single count output demonstrates you are thinking about automation. Why it impresses: a basic answer provides separate SQL queries. A great answer provides a single, orchestrated query, can clearly articulate the use cases for Great Expectations versus DQ, and proposes the advanced quarantine strategy as a resilient alternative to hard failures. AWS well-architected connection: this directly addresses the reliability pillar. Implementing automated data quality checks is a foundational practice for building reliable systems that produce accurate and trustworthy data, which is essential for any analytics platform. Here's a challenge for you to practice and take your skills to the next level for interviews. Implement the quarantine strategy using PySpark. Write a function that reads a data frame, applies a series of quality checks, for example, user_ID is not null, amount a 0, and then returns two separate data frames, one with the clean records and one with the invalid records. This is a common pattern for building reusable data quality components in ETL jobs.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or bow to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Transition to Level 3, Advanced. So far, you've mastered applied AWS plus Python transformations. But now we scale up. Level 3 is where advanced engineers live, optimizing partitioning, fixing Spark data skew, handling schema evolution, and designing CDC pipelines. This is where interviews stop being about syntax and start being about scale. Whiteboard Challenge 9, Counting Distinct Users in a 50 GB CSV on S3. Question: what is this challenge and why does it matter? Answer: this is a quintessential big data interview question. The 50 GB CSV is a deliberate keyword. It is a file size guaranteed to be larger than the RAM of a standard machine. This forces the candidate to immediately discard single machine tools like Pandas and justify a distributed framework like Spark or AWS Glue. This problem tests fundamental concepts, understanding memory limitations, distributed reads from cloud storage, and performing large-scale aggregations. Acing this proves you know how to choose the right tool for the job. The challenge and time box. You have 12 to 15 minutes. A 50 GB CSV file containing user events is stored in S3. Write a PySpark script, as you would for an AWS Glue or EMR job, to efficiently read this file and calculate the total count of distinct user_IDs. You must first explain why a standard library like Pandas is not a viable option. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. Inside the function, we use spark.read.csv to load the data. Spark reads the file in manageable chunks, or partitions, across the worker nodes of the cluster, avoiding memory overload. This is a critical optimization. We select only the user_ID column. This projection pushdown significantly reduces the amount of data that needs to be shuffled across the network for the next step. This is the core logic. Distinct parentheses is a wide transformation that triggers a distributed shuffle to group identical values. Count parentheses is the final action that triggers the job and returns the result. We start the example execution block, which is the standard entry point for a PySpark job script. We initialize the Spark session, giving our job a name for monitoring in the Spark UI. This session manages the connection to the Spark cluster. We define the S3 path to our large CSV file. Spark has a native S3 connector that allows it to read directly from this path in a distributed fashion. Here, we call our main function, passing in the Spark session and the file path to execute the distinct count logic. After the job completes and returns the result, we print the final count to the logs. This serves as a clear confirmation of the job's output. Finally, we gracefully stop the Spark session. This is a best practice that releases all the cluster resources used by the application. Follow-up questions. Follow-up question 1. Before writing the Spark code, you mentioned not to use pandas. Can you elaborate on why? Answer: the primary reason is memory. Pandas is a single machine library, meaning pandas.read_csv parentheses would try to load the entire 50 GB file into the RAM of the machine running the script. A 50 GB file on disk can easily expand to over 100 GB in memory, which would cause the process to crash with an out-of-memory error. Spark is a distributed framework designed for this scale. It processes the file in smaller, manageable partitions across a cluster of machines, so no single machine ever needs to hold the entire dataset. Follow-up question 2. What if you were forced to solve this on a single machine with only 8 GB of RAM and no Spark cluster? Answer: this is a great constraint question. You cannot load the data, so you must stream it. I would use Boto3's get_object and iterate over its streaming body line by line, parsing out just the user_ID. The main challenge is counting distinct IDs without running out of memory. Storing them in a Python set would still fail. The correct approach is to use a probabilistic data structure like a hyperlog log. This allows you to estimate the distinct count with a very high degree of accuracy while using a tiny, fixed amount of memory. Follow-up question 3. Curveball: your Spark job works, but it is very slow. The distinct parentheses stage takes hours. What's the likely cause, and how would you optimize it? Answer: a slow distinct parentheses on a large dataset is almost always caused by a massive data shuffle. The most fundamental optimization is to change the file format. If this is a recurring job, my first action would be to convert the 50 GB CSV to Parquet. When Spark reads a Parquet file, it can perform columnar pruning, meaning it only reads the bytes for the user_ID column from disk. With a CSV, it must read every single byte of all 50 GB just to find that one column. This simple change would drastically reduce the I/O and data sent over the network during the shuffle, making the job much faster. How to ace this whiteboard challenge? How to explain it: immediately identify the 50 GB size as a memory constraint that rules out pandas. Frame Spark as the industry standard tool for this scale. Walk through the Spark code, emphasizing the distributed read and the shuffle caused by distinct parentheses. Why it impresses: a good answer provides the Spark code. A great answer also brings up the advanced Boto3 streaming with hyperlog log, showing deep algorithmic knowledge. Most importantly, identifying the file format, CSV versus Parquet, as the primary performance bottleneck demonstrates senior-level, systems-level thinking. AWS well-architected connection: this directly connects to the performance efficiency pillar. Choosing the right tool, Spark on Glue or EMR, and the right data format, Parquet, for a given workload are core principles of building high-performance, efficient systems on AWS. Here's a challenge for you to practice and take your skills to the next level for interviews. The 50 GB CSV file is poorly formatted. Some rows have extra commas, and some user_ID fields are malformed. Modify your Spark read.csv parentheses call to handle these issues gracefully. Specifically, use options that will prevent the job from failing and instead place any corrupted records into a separate string column named _corrupt_record for later inspection. Whiteboard Challenge 10, Fixing Data Skew in a Large Spark Join. Question: what is this challenge and why does it matter? Answer: data skew is the silent killer of Spark jobs. It happens when data is unevenly distributed across partitions, causing one task to get a disproportionate amount of data. During a join, this means one executor gets stuck processing a massive, hot partition while others sit idle, bottlenecking the entire job. Interviewers love this question because it tests if you understand Spark's execution model beyond just writing code. Fixing skew demonstrates senior-level, system-aware thinking. The challenge and time box. You have 15 minutes. You are joining a large, skewed events data frame with a smaller user's data frame on user_ID. The key, guest_user represents 50% of the events. Explain and code the salting technique to mitigate this skew. Also, mention a simpler alternative you would try first. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We begin by initializing a Spark session, which is the entry point for any Spark application. We give it a name for easier identification in monitoring tools. Next, we create sample data to simulate our problem. The events_data is deliberately skewed, the guest_user key appears much more frequently than others. We then create Spark data frames from this sample data. We define our known skewed key and a salt_factor. This factor determines how many subpartitions we will create to distribute the skewed data more evenly. Our first and simplest technique is a broadcast join. By wrapping the smaller users_df with broadcast parentheses, we tell Spark to send a full copy of it to every worker. This completely avoids a data shuffle on the large events_df, thus avoiding the skew problem. For the salting technique, we first modify the large data frame. We add a random number, salt, from 0 to 3. For any row with the skewed key, we create a new join key like guest_user_0, guest_user_1, etc. This breaks the single large key into multiple smaller keys. On the smaller data frame, we must ensure it can join with all the new salted keys. We do this by taking the single guest_user row and exploding it into 4 rows, creating guest_user_0, guest_user_1, etc., then unioning it back with the non-skewed data. Finally, we perform the join on our new salted_user_ID. Spark will now distribute the join for the guest_user data across 4 different tasks, eliminating the bottleneck. Both the broadcast and salted joins produce the same logical result with 6 rows. The key difference is performance. A naive join would be slow due to one task handling all 4 guest_user events. The broadcast join is fast because it avoids shuffling. The salted join is also fast because the 4 guest_user events are now distributed across different salted keys, for example, guest_user_0, guest_user_2, allowing the join to happen in parallel. Follow-up questions. Follow-up question 1. How do you detect data skew in a real EMR or glue job? Answer. The primary tool is the Spark UI. I would go to the Stages tab and look for the join stage. The classic sign of skew is seeing most tasks complete in seconds, while one or a few straggler tasks take minutes or hours. Clicking into a slow task and viewing its metrics, for example, shuffle read size, will confirm it is processing far more data than its peers. The event timeline also provides a great visual for this. Follow-up question 2, salting and broadcasting are great. What other method does modern Spark provide to handle this automatically? Answer: Modern Spark 3.0 Plus provides adaptive query execution, AQE. One of its key features is spark.sql.adaptive.sqjoin.enabled. When enabled, Spark can detect skew during a shuffle sort merge join at runtime. If it finds a partition that is too large, it can automatically split that partition into smaller subpartitions and replicate the corresponding key from the other side to match. It is essentially an automated, more dynamic version of salting. Follow-up question 3, curveball: what if the skew is not on a specific value but on null values in the join key? How would you handle that? Answer: skew on null keys is a common trap. All null values get sent to the same partition during a shuffle, creating a massive bottleneck. The best approach is to handle them explicitly before the main join. 1. Filter out. If null key records aren't needed for the join, filter them out from both data frames first. This is the simplest fix. 2. Isolate and union. If you need to keep the null records from the large table, you can filter them into a separate data frame, perform the main join on the non-null data, and then union the null key records back into the final result. This prevents them from participating in the expensive, skewed join. How to ace this whiteboard challenge? How to explain it? Start by defining data skew as a hot partition problem. Present the hierarchy of solutions. First, always try a simple broadcast join. If that's not possible, then implement salting. Finally, mention AQE as the modern, automated solution. Why it impresses: a good answer explains salting. A great answer can implement the full salting logic, salting both sides, diagnose the problem with the Spark UI, and knows about modern features like AQE. This demonstrates a deep, practical understanding of Spark internals. AWS well-architected connection. This is a textbook example of the performance efficiency pillar. A skewed job on an EM or cluster can run for hours, wasting huge amounts of money. Fixing skew reduces runtime from hours to minutes, directly optimizing compute cost and resource utilization. Here's a challenge for you to practice and take your skills to the next level for interviews. Automate the salting process. Write a function that first profiles a data frame to identify skewed keys, for example, keys that represent more than 20% of the data. Then, use that discovered list of skewed keys to apply the salting transformation dynamically, without having to hard-code the key values.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or both to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, Dynamo, DB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python data engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 11, Handling Schema Evolution in an AWS Glue/Spark Job. Question: what is this challenge and why does it matter? Answer: schema evolution is when your source data structure changes, new columns are added, old ones are removed, or types change. In the real world, producers constantly evolve their APIs and data formats. A naive ETL job with a fixed schema will break the moment a producer adds a new field. This challenge tests your ability to build resilient pipelines that can gracefully handle these changes. It separates engineers who build brittle jobs from those who design robust, future-proof data platforms. The challenge and time box. You have 12 to 15 minutes. An AWS Glue job reads daily partitioned JSON files from S3. An upstream producer has added a new field, device_type, causing issues. Show in code how you would modify the Spark job to handle this, and then discuss the architectural patterns to manage this problem at scale. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We start by initializing our Spark session, the entry point for our Spark application. We create a realistic scenario by writing two partitions of data. The first partition for date equals 2023-11-23 has the old schema, and the second for date equals 2023-11-24 has the new device_type column. This demonstrates the problem. A standard spark.read.json parentheses call on the parent directory will infer the schema from one of the partitions. It often misses columns that only appear in other partitions. This is the tactical solution. By adding .option, merge schema, true, we instruct Spark to scan all underlying files and merge their individual schemas into a complete superset schema. When we display the result of the brittle read, we can see the device_type column is completely missing. The schema only contains event_ID and user_ID. In the resilient reads output, the schema correctly includes device_type. Spark automatically fills the value with null for the older record that did not have this field, ensuring a consistent data frame structure. The output clearly demonstrates the solution. The first table, from the brittle read, is missing the device_type column entirely. The second table, using merge schema, correctly includes the new device_type column and automatically fills the missing value from the old data with null. This is the desired behavior for a resilient pipeline. Follow-up questions. Follow-up question 1. What is the performance downside of using merge schema equals true? Answer: while convenient, it can significantly slow down job startup time. Spark must perform an extra pass over the data, potentially scanning thousands of file footers, to discover and reconcile the full schema. For ad hoc analysis it is fine, but in a time-sensitive production job, the latency it adds can be a major issue. A predefined schema is always more performant. Follow-up question 2, merge schema is reactive. What is a proactive, enterprise-grade pattern to manage schema changes between producers and consumers? Answer: the proactive solution is to implement a schema registry, like the AWS Glue Schema Registry. This acts as a centralized contract for data schemas. 1. Producers register their schema, for example, Avro, Protobuf, before writing data. 2. Consumers fetch the schema from the registry to read the data. Crucially, you can enforce compatibility rules, for example, backward compatibility, which allows adding new fields but not deleting old ones. This prevents schema-breaking changes from ever reaching the data lake, turning a reactive runtime problem into a proactive governance solution. Follow-up question 3, curveball: what if new fields appear daily and you cannot rely on producers to use a registry? How do you design your data lake to be robust? Answer: this requires a multi-layer data lake design. 1. Raw/landing zone. Ingest the raw JSON data exactly as it comes, with no schema enforcement. This is your schema on read layer. 2. Glue crawler. Run a daily glue crawler on this raw zone. The crawler is designed to detect schema changes and update the glue data catalog table. 3. Curated/processed zone. Have a daily ETL job that reads from the raw zone, using the updated glue catalog schema, and writes to a processed zone in a well-defined Parquet format. This job is responsible for cleaning, standardizing, and handling nulls from evolved schemas. This separates ingestion from consumption, ensuring the raw data is always preserved while the curated data remains stable for analytics. How to ace this whiteboard challenge? How to explain it? Start by showing the problem with a simple code example. Introduce merge schema as the immediate fix. Then, elevate the conversation to architecture by discussing the limitations of merge schema and presenting the schema registry as the superior, proactive solution. Why it impresses: a good answer shows how to use merge schema. A great answer discusses the full architectural lifecycle, the reactive fix, merge schema, the proactive fix, schema registry, and the resilient data lake design, raw versus curated zones with a glue crawler. This demonstrates senior-level, end-to-end thinking. AWS well-architected connection. This directly addresses the reliability pillar. A pipeline that can handle schema evolution is inherently more reliable. Discussing a schema registry and multi-zone S3 design also demonstrates the operational excellence pillar by establishing automated governance and clear data contracts. Here's a challenge for you to practice and take your skills to the next level for interviews. A producer has made a breaking change. They renamed the user_ID column to customer_identifier. Your job is now failing. Merge schema will not fix this. Write a PySpark function that can gracefully handle this change. It should inspect the incoming data frames columns and, if it finds customer_identifier, it should rename it to the standard user_ID before proceeding with the rest of the transformations. Whiteboard Challenge 12, Optimizing a billion-row S3 data lake for Athena. Question: what is this challenge and why does it matter? Answer: this is a fundamental cloud data architecture challenge. Simply dumping billions of rows of Parquet files into S3 creates a data swamp where queries are slow and expensive because they perform full table scans. This question tests your ability to design a data layout that is query-aware. By correctly applying partitioning, bucketing, and compression, you can reduce query times from hours to seconds and cut Athena costs by over 99%. This knowledge is the difference between building a barely usable data lake and a high-performance, cost-effective analytics platform. The challenge and time box. You have 10 to 15 minutes. An events table with billions of rows is stored as Parquet in S3, and Athena queries are slow and costly. Your task is to write a single create table DDL statement that applies the three core optimization techniques: partitioning, bucketing, and compression. Explain how each technique works to reduce costs and improve speed. Here is the SQL implementation I would use. Disclaimer: always test code in a non-production environment. This is the most important optimization. We partition by country_code and event_date. This physically organizes the data in S3 into folders like /country_code equals US/event_date equals 2023-11-25/. A query with a where clause on these columns will only scan files inside those specific folders, a technique called partition pruning. This is bucketing. Within each partition folder, we split the data into 32 files based on a hash of the user_ID. All records for a given user_ID will always land in the same file, for example, file_05_. This drastically speeds up joins and group by operations on user_ID by avoiding full scans of all files in the partition. We explicitly define the storage format as parquet. This is a columnar format, which means a query like select sum, revenue, only needs to read the revenue column, not the entire row, making it extremely efficient. Finally, we specify snappy compression. It offers a great balance of compression ratio and fast decompression speed, and most importantly, it is splittable, which is essential for parallel processing by distributed engines like Athena and Spark. The impact is dramatic. Partition pruning alone can reduce the data scanned, and therefore the cost, by orders of magnitude. Bucketing further accelerates joins, reducing overall query runtime. This is how you build a cost-effective data lake. Follow-up questions. Follow-up question 1. How do you choose between partitioning and bucketing for a column? Answer: it comes down to cardinality and query patterns. Partitioning is for low to medium cardinality columns that are frequently used for filtering in where clauses, for example, date, country, status. Bucketing is for high cardinality columns that are frequently used in join keys or group by aggregations, for example, user_ID, product_ID. Using a high cardinality key for partitioning would create too many small files and hurt performance. Follow-up question 2. Your DDL defines the metadata. What AWS service actually writes the data to S3 in this specific layout? Answer: an AWS Glue ETL job is the perfect service for this. The job would be written in PySpark. You would read the raw source data into a data frame and then use a command like df.write.partition by country_code, event_date, .bucket by 32, user_ID, .save as table, optimized_events. This command instructs Spark to perform the necessary shuffling and hashing to write the parquet files into the exact S3 folder structure that the DDL expects. Follow-up question 3. Curveball: a query filters on product_ID, which is a high cardinality column and not suitable for partitioning. How can you optimize this query without changing the partitions? Answer: this is where the power of the parquet file format itself comes in. Parquet files store statistics, like min/max values, for each column in their footer metadata. When Athena receives a query like where product_ID equals prod_123, it can first read the file footers. If the min/max range for product_ID in a specific file does not include prod_123, Athena can skip reading that entire file. This is called predicate pushdown and can dramatically reduce data scanning without any extra partitioning. How to ace this whiteboard challenge? How to explain it? This is a design question. Start by explaining the problem. Full scans are slow and expensive. Present the three solutions in order of importance. 1. Partitioning, for where. 2. Bucketing, for joins. 3. Compression/format, for I/O. Use the DDL to structure your explanation. Why it impresses: a good answer lists the three techniques. A great answer can clearly explain the difference between partitioning and bucketing, knows how to choose good partition keys, cardinality, and can describe how the physical files are actually created by an ETL job. Mentioning predicate pushdown shows a deep understanding of file formats. AWS well-architected connection. This is a perfect example of the cost optimization and performance efficiency pillars. Every technique discussed directly reduces the amount of data scanned, cost, and the time it takes for a query to complete, performance. This is the essence of data lake architecture on AWS. Here's a challenge for you to practice and take your skills to the next level for interviews. You are designing a new data lake table for customer order data. The most common query patterns are, 1. Finding all orders for a specific customer, user_ID, 2. Analyzing all orders within a specific month, order_month. The user_ID has very high cardinality, while order_month has low cardinality. Write the create table DDL for this orders table, applying the optimal partitioning and bucketing strategy based on these query patterns.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this, you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or bow to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, You people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 13, Designing a CDC Pipeline from an OLTP Database to Redshift. Question: What is this challenge and why does it matter? Answer: Change Data Capture, CDC, is the modern solution for keeping an analytical data warehouse like Redshift in sync with a transactional database, like PostgreSQL or MySQL. The old way was slow, expensive nightly batch dumps. CDC is far more efficient. It captures row-level changes, inserts, updates, deletes, in near real time. This challenge tests your ability to design a full-stack AWS data pipeline, requiring knowledge of specific services, DMS, warehousing concepts, upserts, and the architectural patterns needed to handle a continuous stream of changes. The challenge and time box. You have 15 to 20 minutes. A production RDS database powers an e-commerce application. You need to replicate the orders table to a Redshift warehouse for analytics. Design the AWS pipeline and write the SQL logic used in Redshift to apply these changes. High-level CDC architecture. 1. Source OLTP, RDS application database where inserts, updates, deletes occur. 2. AWS DMS, reads the database transaction logs, binlog/WAL, to capture changes with low impact. 3. Staging area, S3 DMS writes change records, for example, CSV/Parquet, marked with an operation type, IUD. 4. Load to staging, Redshift and orchestrator, step functions/Airflow, uses a copy command to load new files from S3 into a temporary staging table in Redshift. 5. Apply changes, Redshift a merge command is run to atomically apply the inserts, updates, and deletes from the staging table to the final target table. Here is the SQL implementation I would use. Disclaimer: always test code in a non-production environment. First, we define a staging table in Redshift. This table will temporarily hold the batch of change records loaded from S3. The critical column here is op, which DMS adds to tell us if a row was inserted, updated, or deleted. The merge command is the heart of the logic. It joins our permanent target table with the source staging table on the primary key, order_ID, to identify which records need to be inserted, updated, or deleted. This clause handles updates. If a record from the staging table finds a match in the target table and its operation flag is U, we update the target records columns with the new values from the source. This clause handles deletes. If a matching record is found and the operation flag is D, the delete command removes that record from the target table entirely. This clause handles new records. If an order_ID from the staging table does not exist in the target table and its operation flag is I, we perform an insert to add it as a new row. Follow-up questions. Follow-up question 1. How does AWS DMS capture changes efficiently without adding heavy load to the production database? Answer: this is the key advantage of log-based CDC. AWS DMS taps into the database's native transaction log, the write-ahead log in Postgres or bin log in MySQL. This log is a low-level stream of all committed changes that the database itself uses for replication and recovery. By reading this log, DMS captures every insert, update, and delete with minimal performance impact on the source database, unlike traditional query-based methods. Follow-up question 2. The merge command can be slow if you are applying a million changes to a billion-row table. How would you scale this process? Answer: that's a great performance tuning question. The key is to reduce the batch size and run more frequently. Instead of one large hourly merge, I would design the orchestrator to trigger microbatches every 5 minutes. This keeps the staging table small and allows the merge to complete very quickly. For extremely high volume, real-time needs, you would consider a hybrid architecture, DMS to Kinesis to Lambda to DynamoDB for the hot latest state, with a separate, less frequent load into Redshift for historical analytics. Follow-up question 3. curveball: what if you do not want to perform hard deletes in your warehouse for historical or compliance reasons? How would you modify your design? Answer: this is a classic data warehousing requirement for building a Type 2 slowly changing dimension, SCD2. Instead of using delete, you would perform a soft delete. We would add 2 columns to our Redshift table, is_active, a boolean, and valid_to, a timestamp. When a D operation comes from DMS, the merge logic changes. Instead of delete, it becomes an update that sets is_active equals false and valid_to equals current_timestamp for that record. This preserves the full history, allowing analysts to query the data as it existed at any point in time. How to ace this whiteboard challenge? How to explain it? This is a system design question. Start with the high-level architecture diagram. Clearly explain the role of each component, DMS for capturing, S3 for staging, and Redshift for applying changes. Then, write the merge statement as the specific implementation. Why it impresses: a good answer describes DMS and writes an upsert. A great answer can also articulate the performance trade-offs, microbatching, the streaming alternative, kinesis, and advanced data warehousing concepts like soft delete/SCD2. This shows you understand both the tools and the theory. AWS well-architected connection: this pipeline exemplifies the reliability pillar. It is based on the transaction log, the source of truth, and performance efficiency. It avoids expensive full table dumps by processing only incremental changes. Here's a challenge for you to practice and take your skills to the next level for interviews. The merge command is powerful but can be slow on very large tables if the staging table is large. An alternative is the delete and insert pattern. Write a multi-statement SQL transaction that achieves the same result as the merge command but using separate delete and insert statements. What are the potential risks or downsides of this approach compared to a single merge command? Level 4, Expert Level, capstone challenges that really test end-to-end thinking. So far, we've mastered the core building blocks, algorithms, SQL patterns, and AWS data transformations. We went deeper into advanced territory with partitioning, schema evolution, and CDC pipelines, showing what it really takes to work at scale. But now, we're stepping into the arena where senior engineers live: system design, streaming, and security. This is the final level, the expert phase, where every decision you make has platform-wide implications. From building real-time streaming pipelines to securing data lakes with IAM and designing Netflix-scale architectures, this is where whiteboard challenges transform into real-world leadership conversations. Buckle up, Level 4 is where you prove you're not just an engineer, but an architect. Whiteboard Challenge 14, Building a Real-Time Tweet Filtering Pipeline on AWS. Question: what is this challenge and why does it matter? Answer: this is a quintessential senior-level system design question that tests your ability to architect event-driven, serverless data flows on the cloud. The ability to ingest, process, and store a real-time data stream is a core competency for modern data engineers. Acing this does not just show you can write Python, it proves you can build scalable, resilient, and cost-effective data pipelines using managed AWS services, a far more valuable skill. The challenge and time box. You have 15 to 20 minutes. Design an end-to-end, serverless pipeline on AWS that ingests a stream of tweets, filters them in real time for specific keywords, for example, AWS, Python, and stores the matching tweets in a structured S3 data lake. You must design the architecture and then write the core Python code for the processing logic. Gold standard architecture, serverless streaming pipeline. 1. Producer, for example, EC2 or ECS connects to a source like the Twitter API and pushes tweet data into an Amazon Kinesis data stream. 2. Buffer, Amazon Kinesis acts as a highly scalable, real-time buffer that decouples the producer from the consumer. 3. Consumer or processor, AWS Lambda. A Lambda function is automatically invoked with microbatches of tweet records from the stream. 4. Filtering and enrichment. Lambda code. The function's code decodes the records, applies a keyword filter, and enriches the data. 5. Data lake storage. Amazon S3. The Lambda function writes the filtered tweets as partitioned JSON files into an S3 bucket, ready for analytics. Here is a AWS-style architecture diagram: tweets to Kinesis to Lambda to S3 bucket to Athena or Glue/Redshift. This diagram illustrates a Netflix-scale, real-time data processing architecture using AWS services. Producer, tweets or event stream. An event stream is continuously sent into Amazon Kinesis, which acts as a high-throughput ingestion layer. Consumer and processing, AWS Lambda function. A Lambda function is triggered in real time by Kinesis, containing Python code to filter incoming records. Storage, Amazon S3. The filtered data is written by Lambda into Amazon S3, partitioned by date to optimize for analytical queries. Analytics, Amazon Athena and Amazon Redshift. From S3, the data can be queried interactively with Athena or loaded into Redshift for more complex data warehousing. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We initialize the S3 client and load configuration from Lambda environment variables outside the handler function. This is a crucial performance best practice, allowing Lambda to reuse these initialized objects across multiple invocations. Inside the handler, we initialize an empty list. This will hold the tweets from the current batch that match our filter criteria. We start a loop to iterate through each record in the batch that the Lambda function receives from Kinesis. Inside the loop, for each record, we decode the JSON payload, parse it into a Python dictionary, and extract the tweet's text for filtering. This is our core logic. We check if any keyword exists in the tweet's text. If it is a match, we enrich the tweet with a processing timestamp and append it to our filtered_tweets list. After the loop finishes, we check if our list of filtered tweets contains any records. If it does, we proceed to write them to S3. Inside the if block, we generate a highly structured S3 object key. We use Hive-style partitioning, year equals, /month equals, which makes the data instantly queryable by Athena. A unique timestamp filename prevents collisions. We then write the entire batch of filtered tweets to S3 in a single put_object call. Writing in batches like this is more efficient than writing one file per tweet. Finally, the Lambda handler returns a success status and the count of filtered tweets. This is useful for logging and monitoring in CloudWatch. The output in S3 is a JSON file whose path is partitioned by date. The file itself contains a JSON array of all the tweet objects that matched our filter keywords during that Lambda invocation. This structure is perfectly optimized for subsequent analysis with AWS Athena. Follow-up questions. Follow-up question 1. How does this Kinesis or Lambda architecture scale if tweet volume spikes? Answer: this architecture scales automatically and in parallel. Kinesis scales by adding more shards. Each shard provides a fixed unit of throughput. Lambda scales by increasing concurrency. The Lambda service will automatically spin up more instances of our function, one for each active Kinesis shard, to process the data in parallel. This decoupling of buffer and compute is the key to its scalability. Follow-up question 2. What happens if your Lambda function fails due to a malformed tweet record? How do you prevent blocking the entire stream? Answer: this is a critical reliability question. To prevent a single poison pill record from halting the pipeline, I would configure the Lambda's event source mapping with a dead letter Q, DLQ, pointing to an SQSQ. If a batch of records fails repeatedly, after the configured number of retries, the entire batch is sent to the DLQ. This gets the bad data out of the main stream so good data can continue to flow, and we can inspect the failed batch later for debugging. Follow-up question 3. Curveball: what if you needed to power a real-time dashboard showing trending hashtags, updated every 10 seconds? Answer: S3 is not the right tool for that, it is for batch analytics. I would add a second, parallel consumer to the same Kinesis stream. I would use Amazon Kinesis Data Analytics, which runs Apache Flink, to read the stream, perform a tumbling window aggregation to count hashtags every 10 seconds, and then write the results to a low-latency database like Amazon DynamoDB or Elasticache, Redis. The dashboard would then query this low-latency store, not S3. How to ace this whiteboard challenge? How to explain it? Start with the high-level, three-part architecture: producer to buffer, Kinesis, points to consumer, Lambda, points to storage, S3. This shows you think in systems. Then, code the Lambda consumer, being sure to mention production best practices like using environment variables and structured S3 keys. Why it impresses: a gold standard answer shows the entire data flow, explains the scaling mechanism, shards or concurrency, and can design a robust error handling strategy, DLQs. Discussing architectural alternatives for different use cases, dashboards versus data lake, is the final touch of a senior engineer. AWS well-architected connection: this design is a masterclass in the AWS pillars. It is operationally excellent, serverless, reliable, Kinesis durability, DLQs, performance efficient, parallel processing, and cost optimized, paper invocation. Here's a challenge for you to practice and take your skills to a next level for interviews. Modify the Lambda function to be more efficient for data lake querying. Instead of writing one JSON file containing a list of tweets, write a single JSON lines file, .soml, where each line is a separate, self-contained JSON object representing one tweet. Why is the JSON lines format often superior to a single large JSON array for distributed query engines like Athena and Spark?
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or Bo to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 15, Guaranteeing Event Order in a Kinesis Streaming Pipeline. Question: what is this challenge and why does it matter? Answer: ordering is one of the hardest problems in distributed streaming. Events often arrive out of order due to network latency or producer retries. For many use cases, like clickstream session analysis or financial transaction processing, processing events in the wrong sequence leads to incorrect results and business logic failures. This challenge tests your deep understanding of a streaming system's guarantees and your ability to architect a solution that balances correctness, scalability, and latency. The challenge and time box. You have 15 to 20 minutes. A Kinesis stream ingests user clickstream data where events can arrive out of order. Your task is to design a pipeline that correctly calculates the duration of user sessions. First, explain the Kinesis native mechanism for ordering. Then, design and pseudocode a Spark structured streaming application that uses watermarking to solve the problem. Gold standard architecture, stateful stream processing. 1. Producers, send clickstream events to Kinesis, using session_ID as the partition key. 2. Kinesis data stream, guarantees that all events for the same session_ID go to the same shard, preserving their relative order. 3. Consumer, AWS Glue or EM or with Spark. A Spark structured streaming job consumes data from Kinesis. 4. Stateful logic, watermarking and windowing. The Spark application defines a watermark, a threshold for lateness. It groups events by session within a time window. 5. State store, managed by Spark. Spark maintains an in-memory or on-disk state for each active session, holding onto events until the watermark confirms no more late data will arrive for that window. 6. Sync, S3 or Analytics DB. Once a session window is finalized, the correctly calculated session duration is written to the destination. Here is a WS-styled flowchart with producers, Kinesis shards, Lambda plus buffer, storage. If you don't know this nuance, that Kinesis guarantees order only inside a shard, you'll fail this interview question instantly. Let me show you how to fix it with partition keys and watermarking. So here's the catch with Kinesis: you only get ordering guarantees within a shard. If you want ordered sequences, you must design your partition keys carefully, session_ID, user_ID, or device_ID, so that related events always land in the same shard. But even then, you'll still see small hiccups where events arrive late due to retries or network lag. That's where watermarking comes in. By buffering events for, say, 30 seconds, and then flushing them in sorted order, you can deliver nearly perfect event time ordering while still staying real-time enough for analytics. Here is the Python implementation I would use. Disclaimer: always test code in a non-production environment. We begin by setting up a Spark structured streaming reader to consume data from our Kinesis stream. This creates a continuously updating data frame. This is the core of the out-of-order solution. We define a watermark on the event_timestamp column. This tells Spark's engine, do not finalize any time-based calculations until you are certain that no more events with timestamps older than 10 minutes from the latest event will arrive. We group our data by two keys, a 30-minute tumbling window based on the event time, and the session_ID. The watermark ensures that Spark will keep the state for each of these windows open long enough to accommodate late arriving events. Within each group, we perform our aggregation. We find the earliest and latest timestamps for that session and calculate the duration. Because of the watermark, this calculation will be correct even if the max event arrived before the min event. Finally, we write the output. Output mode, append, is used with watermarking. It ensures that Spark only writes the final, aggregated result for a window once the watermark has passed its end, guaranteeing the calculation is complete and correct. The output demonstrates the power of watermarking. A naive engine might prematurely calculate the session duration using only the first two events. With a watermark, the engine waits, incorporates the late, click, event into its state, and then computes the final, correct duration for session S1, T10 to 05 to 00, T10 to 01 to 00 equals 240 seconds. Follow-up questions. Follow-up question 1. Before using Spark, what is the most fundamental ordering guarantee Kinesis itself provides? Answer: the most fundamental mechanism is the partition key. Kinesis guarantees that all records sent with the same partition key will be placed into the same shard. Consumers reading from that shard are guaranteed to receive those records in the exact order they were put. The limitation is that Kinesis provides no ordering guarantee across different shards. This is the classic trade-off: use a single partition key for global order but lose scalability, or use many partition keys for scalability but lose global order. Follow-up question 2. What is the business and technical trade-off in setting the watermark duration? Answer: it is a critical trade-off between latency, accuracy, and cost. A short watermark, for example, 1 minute, provides low latency results and requires less memory or state, but you risk dropping events that are more than 1 minute late, sacrificing accuracy. A long watermark, for example, 1 hour, ensures higher accuracy by capturing very late data, but it significantly increases the amount of state Spark must maintain, which increases memory costs, job recovery time, and the latency of your final results. Follow-up question 3. Curveball: what if some events can arrive days late, far beyond any reasonable watermark? How would you achieve eventual correctness? Answer: this requires a lambda architecture or a similar batch reconciliation pattern. 1. Streaming layer, the real-time pipeline with a reasonable watermark, for example, 1 hour, handles the majority of data for low-latency dashboards. 2. Batch layer, a separate, daily batch job runs on the raw S3 data. This job reprocesses the last few days of data, recalculating all session durations with a complete, ordered view. 3. Serving layer, the batch job then uses a merge or upsert operation to update the final analytical tables, correcting any inaccuracies from the streaming layer. This combines the speed of streaming with the correctness of batch. How to ace this whiteboard challenge? How to explain it: start with the Kinesis fundamentals. Partition keys ensure order within a shard. Then, introduce watermarking as the application-level solution for handling cross-shard disorder and general lateness. The Spark code makes the concept concrete. Why it impresses: a good answer explains watermarking. A gold standard answer can articulate the precise role of the partition key first, explain the latency versus accuracy trade-off, and design a batch reconciliation layer, lambda architecture, for achieving eventual correctness. This demonstrates a holistic understanding of streaming systems. AWS well-architected connection: this design directly addresses the reliability pillar. By correctly handling out-of-order data, you build a reliable system that produces accurate results. The discussion on state management and batch reconciliation also touches on performance efficiency and cost optimization. Here's a challenge for you to practice and take your skills to the next level for interviews. Extend the sessionization logic to handle duplicate events. A producer might sometimes send the same event twice due to retries. Modify your Spark aggregation to ensure that duplicate events, defined as having the same session_ID and event_timestamp, are counted only once before calculating the final session duration. Hint: use drop duplicates parentheses before the group by. Whiteboard Challenge 16, Architecting a Secure S3 Data Pipeline. Question: what is this challenge and why does it matter? Answer: security is the most critical, non-functional requirement in data engineering. A data breach of sensitive customer information can be catastrophic. This challenge moves beyond simple data processing and tests your ability to act as a steward of that data. It requires you to apply the principle of least privilege across multiple AWS services to build a pipeline that is secure by design. Acing this does not just show you know AWS, it proves you can be trusted with a company's most valuable asset, its data. The challenge and time box. You have 15 to 20 minutes. Design the security architecture for an ETL pipeline where an AWS Glue job reads sensitive raw data from one S3 bucket, processes it, and writes the transformed data to another S3 bucket. You must design the IAM roles, S3 bucket policies, and encryption strategy to ensure end-to-end security and enforce least privilege. Gold standard security architecture, a least privilege data pipeline. 1. Raw S3 bucket stores the initial sensitive data. It is encrypted with a customer-managed KMS key. A strict bucket policy denies all access by default. 2. AWS Glue ETL job runs under a specific IAM role, Glue ETL role. This role is granted the bare minimum permissions needed to perform its task. 3. Glue role permissions. The IAM role has a policy that allows it to S3 get object from the raw bucket. S3 put object to the processed bucket. KMS decrypt using the KMS key to read raw data. KMS encrypt using the KMS key to write processed data. 4. Processed S3 bucket stores the transformed, clean data, also encrypted with the same KMS key. Its bucket policy also denies access by default, but has exceptions for consumers. 5. Analyst, consumer accesses the data via a separate analytics role, which only has S3 get object permissions on the processed bucket and KMS decrypt permission on the key. This role has no access to the raw bucket. Here is a AWS-styled security diagram. Here's how we secure sensitive data in an AWS pipeline. Data first lands in an S3 ingestion bucket, but the bucket has strict controls, encryption at rest using a KMS customer-managed key, TLS-only access, and bucket policies that deny public traffic. Next, downstream services like AWS Glue or Lambda don't use static credentials. Instead, they assume least privilege IAM roles scoped only to the resources they need. This ensures no developer keys or over-permissioned roles are floating around. When the data is processed and loaded into Redshift Spectrum or downstream systems, the same security model applies, IAM role chaining plus KMS integration for decryption. Finally, every access is audited with CloudTrail and S3 access logs, so auditors know exactly who touched which file and when. This architecture nails the AWS well-architected security pillar, encryption everywhere, strict least privilege, and full traceability. It's not just moving data, it's moving data securely at scale. Here is the JSON implementation I would use. Disclaimer: always test code in a non-production environment. First, we define the IAM policy. This is identity-based and specifies what the Glue job's role is allowed to do. It is a list of permissions. The policy document grants 3 specific permissions: get object on the raw bucket, put object on the processed bucket, and the ability to use our specific KMS key for encryption and decryption. This is a perfect example of least privilege. Next, we define the S3 bucket policy. This is resource-based and acts as a powerful guardrail for the bucket itself, providing defense in depth. This first statement in the bucket policy is a critical best practice. It denies any S3 action if the connection is not encrypted with TLS, that is, not using HTTPS. This protects data in transit. The second statement explicitly grants GetObject access only to our specific Glue job's IAM role. By not having a general allow for anyone else, we ensure that only this principal can access the raw data, even if other roles have overly permissive IAM policies. Follow-up questions. Follow-up question 1. You have used both an IAM policy and a bucket policy. Why is this defense in depth strategy necessary? Answer: they serve two different purposes and create overlapping layers of security. An IAM policy is identity-based. It is attached to a user or role and defines what actions that identity can perform across AWS. An S3 bucket policy is resource-based. It is attached to the bucket and defines who can access that specific resource. Using an explicit deny in the bucket policy acts as a powerful guardrail that can override even a permissive IAM policy, preventing accidental exposure. You can be certain that only the intended role can access the raw data. Follow-up question 2, you chose KMS for encryption. What is the difference between SSES3 and SSEKMS, and why is SSEKMS generally preferred for sensitive data? Answer: SSES3 uses encryption keys that are fully managed by Amazon S3. It is simple and effective, but you have no control or visibility into the key. SSEKMS uses keys that are managed within the AWS Key Management Service, KMS. This is superior for sensitive data because it provides 1. Centralized control and audit. You can define who can use the key via key policies. Every use of the key is logged in AWS CloudTrail. 2. Key rotation. You can enable automatic annual rotation of the cryptographic material. 3. Granular permissions. You can grant KMS decrypt permission to consumers without granting them any other permissions. This separation of duties is a key security principle. Follow-up question 3, curveball: how would you prevent data from ever leaving your company's private network, even if an IAM role with S3 access was compromised on a public EC2 instance? Answer: this requires network-level security using VPC endpoints. I would create an S3 gateway endpoint for my VPC. Then, I would modify the S3 bucket policy to add a condition that denies all access unless the request comes through that specific VPC endpoint. The policy would look like, condition, string not equals, AWS, source VEPS, VEPS1A2B3C4D. This ensures that even with valid credentials, the data cannot be exfiltrated because the S3 bucket will reject any API call that does not originate from within our private network. How to ace this whiteboard challenge? How to explain it: start with the principle of least privilege. Draw the architectural diagram and explain the data flow. Then, detail the security controls at each layer: IAM for identity, S3 bucket policies for resource guardrails, and KMS for data protection at rest. Why it impresses: a good answer lists the services. A gold standard answer can write the actual JSON policies, explain the crucial difference between IAM and bucket policies, articulate the benefits of SSEKMS, and can design network-level controls with VPC endpoints. This demonstrates a holistic, multi-layered approach to security. AWS well-architected connection: this challenge is the embodiment of the security pillar. It is all about applying defense in depth, using encryption everywhere, and enforcing the principle of least privilege to protect data and systems. Here's a challenge for you to practice and take your skills to the next level for interviews. An analytics team in a different AWS account needs read-only access to the processed data in my processed data bucket. Design the full cross-account access solution. This will require modifying 3 things: 1. An IAM role in the analytics account, 2. An IAM role in your data account with a trust policy, and 3. The S3 bucket policy and KMS key policy in your data account.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or bow to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 17, Debugging a Glue Job with an Access Denied Error. Question: what is this challenge and why does it matter? Answer: this is one of the most realistic data engineering interview curveballs. You have written the perfect glue job, but it fails with an access denied exception. Debugging IAM is a fundamental AWS skill that tests whether you can untangle policies, roles, and trust relationships under pressure. This challenge simulates real-world firefighting. It proves you can think like a detective and fix permissions without compromising security. The challenge and time box. You have 15 minutes. A daily AWS Glue job has started failing with access denied. Your task is to whiteboard your systematic debugging checklist. You must identify the potential failure points and then propose a gold standard, least privilege IAM policy for the job. The 4 layers of IAM debugging. An access denied error is almost always a mismatch in one of these 4 security layers. A systematic check is the key to solving it quickly. 1. Identity policy, the role's permissions. What is the glue role allowed to do? For example, S3 get object. 2. Resource policy, the bucket or keys permissions. What is the S3 bucket or KMS key allowing to be done to it? 3. Trust policy, the role's assumption policy. Can the AWS Glue service assume this role in the first place? 4. Network policy, VPC endpoints. Is the request coming from an allowed network location? My 5-step debugging checklist, the solution. Step 1. Find the root cause in CloudTrail. My first action is always to go to AWS CloudTrail event history. I will filter by the glue roles ARN and look for events with an error code of access denied. The event record is the source of truth. It tells me the exact API call that failed, for example, S3, put object, the resource it failed on, and a detailed error message. This turns guesswork into a precise investigation. Step 2. Check the IAM roles identity policy. With the failed action from CloudTrail, I will inspect the IAM policy attached to the glue jobs role. I will verify that it has an allow statement for the specific action, S3, put object, on the correct resource ARN, AWS hesitant phase 3, my bucket ***. I will also check for any explicit deny statements, as they always override an allow. Step 3. Check the resource policies, S3 and KMS. If the IAM policy is correct, the problem is likely a resource policy. I will check the S3 bucket policy for any explicit deny statements that might be blocking my glue role. Then, if the bucket is encrypted, I will check the KMS key policy. The KMS key must also have a statement allowing the glue role to perform actions like KMS decrypt. Step 4. Verify the IAM role's trust relationship. If the job fails immediately on startup, the issue is often the trust policy. I will navigate to the Roles, Trust Relationships tab and ensure that glue.amazonaws.com is listed as a trusted service principal. Without this, the Glue service has no permission to assume the role. Step 5. Inspect network and VPC endpoint policies. If all else fails, especially if the job works in one VPC but not another, the issue is likely network-related. I will check the S3 bucket policy for a condition that restricts access to a specific VPC endpoint. The production job might be running outside this allowed network path. IAM role debugging, access denied in Glue job. Imagine this, you launch a Glue job, and instead of running smoothly, it fails with a big red access denied error. This is one of the most common AWS security puzzles in interviews, and in real life. Debugging IAM is about following the chain of permissions step by step. First, always start with the Glue job role. What exact IAM role is the job assuming? Next, check the inline and attached policies. Do they allow the specific S3, KMS, or DynamoDB actions the job needs? Then comes the trust relationship. Is the Glue service even allowed to assume this role? Finally, look for role chaining or cross-account issues. Maybe the Glue job role needs to assume another role to reach its target, and that trust is broken. In short, IAM debugging is like detective work. You don't just look at the error, you trace the entire execution path, job to role to policy to trust to resource. And when you can explain this chain clearly in an interview, you prove you're not just writing jobs, you're building secure, reliable systems. Here is the JSON implementation I would use. Disclaimer: always test code in a non-production environment. This statement grants the absolute minimum required S3 permissions, read access, get object, scoped only to the raw bucket, and write access, put object, scoped only to the processed bucket. If the data is encrypted, the role needs explicit permission to use the KMS key. We grant decrypt for reading and encrypt for writing, scoped to the specific key being used. A production-ready role must also have permissions to write logs to CloudWatch. Forgetting this is a common reason jobs fail silently or with unclear errors. Follow-up questions. Follow-up question 1. What's the key difference between an IAM policy and a resource-based policy, like an S3 bucket policy? Answer: IAM policies are identity-based. They are attached to an identity, a user or role, and define what that identity is allowed to do. Resource-based policies are attached to a resource, like an S3 bucket or KMS key. They define who is allowed to access that specific resource. For an action to be allowed, typically at least one of these must grant permission, and importantly, neither can have an explicit deny. Follow-up question 2. How can you proactively prevent these permission issues in a large team environment? Answer: this requires a shift to infrastructure as code, IAC, using tools like Terraform or CloudFormation. By defining all IAM roles and policies in code, we can enforce peer reviews for any permission changes. We can also integrate automated static analysis tools like IAM Access Analyzer to scan for overly permissive or insecure policies before they are ever deployed to production. How to ace this whiteboard challenge? How to explain it? Present your answer as a systematic, numbered checklist. Always start with CloudTrail to get the facts. Then, methodically check each of the 4 layers: identity, resource, trust, and network. This shows a calm, logical approach to troubleshooting. Why it impresses: a good answer lists a few things to check. A gold standard answer presents a comprehensive mental model for debugging IAM, knows how to use CloudTrail for forensics, and can explain proactive prevention with IAC. It shows you are an operator, not just a developer. AWS well-architected connection. This challenge embodies the operational excellence pillar, the ability to run systems and gain insight into their operations, and the security pillar, applying least privilege and having the ability to trace permissions. Here's a challenge for you to practice and take your skills to the next level for interviews. Using the AWS console, deliberately create a broken setup. Create 2 S3 buckets, raw, processed, and a glue job role. First, break it by giving the role a bad IAM policy. Fix it. Then, break it again with a restrictive S3 bucket policy. Fix it. Finally, encrypt the bucket with a KMS key and break it by forgetting the KMS policy permissions. Document each access denied error and the specific fix you applied. Whiteboard Challenge 18, Designing a Data Model for OLTP and OLAP Workloads. Question: what is this challenge and why does it matter? Answer: this is a quintessential data architecture question that tests your ability to design systems for fundamentally opposed workloads. OLTP, online transaction processing, systems need to handle fast, single-row writes and reads, while OLAP, online analytical processing, systems need to handle massive aggregations. Trying to serve both with a single database is a classic anti-pattern that leads to a slow, expensive system. Acing this proves you can choose the right tool for the right job and design a hybrid architecture that excels at both. The challenge and time box. You have 20 minutes. Design the data models and AWS architecture for a user event system. The system must support 1. A real-time application writing events with low latency, and 2. An analytics team running complex, high-throughput queries. You must design both the OLTP and OLAP schemas and explain how they connect. Gold standard architecture, the hybrid OLTP plus OLAP model. The solution is not one database, but a hybrid system connected by a data pipeline. 1. Ingestion layer, Kinesis or API gateway streams raw user events in real time. 2. OLTP store, Amazon DynamoDB. The application writes events directly to a DynamoDB table, which provides single-digit millisecond latency for writes and key-value lookups. 3. ETL or replication, DynamoDB streams to Lambda to S3. DynamoDB streams captures all changes. A Lambda function processes these changes and writes them to a staging S3 data lake. 4. OLAP store, Amazon Redshift. A periodic ETL job loads the data from S3 into a Redshift data warehouse, transforming it into a star schema optimized for analytics. 5. Query layers, the live application queries DynamoDB. The analytics team queries Redshift. Data modeling for OLTP and OLAP systems. Here's where data engineering meets system design. We're modeling user events in a way that supports both transactional workloads, OLTP, and analytical queries, OLAP. On the left, we have DynamoDB, perfect for OLTP workloads. It captures raw user events, logins, clicks, purchases, at high velocity. The schema here is denormalized for fast writes and real-time lookups. In the middle, we flow data into Amazon Redshift. This is where the OLAP workloads live: aggregations, cohort analyses, trend detection. Redshift is modeled using a star schema, with a central fact table of user events linked to dimension tables like users, devices, and geographies. The arrows represent ETL jobs, using Glue or Spark, transforming DynamoDB streams into clean, queryable data inside Redshift. Notice how the design balances the trade-offs. DynamoDB ensures speed and scale for operations, while Redshift ensures depth and insight for analytics. This is a gold standard hybrid design: write fast in NoSQL, analyze smart in SQL, the essence of modern cloud data modeling. Here is the implementation one using SQL, the OLAP star schema. For Redshift implementation I would use. Disclaimer: always test code in a non-production environment. This is our fact table. It is long and narrow, containing the core facts or measurements like revenue_USD and foreign keys that link to our dimension tables. OLAP queries will primarily aggregate the metrics in this table. This is a dimension table. It is wide and shallow, containing descriptive attributes about a business entity, a user. Analytics queries will join the fact table to this table to group by or filter on attributes like country. For our OLTP system, DynamoDB, we use a key-value model. The partition key, user_ID, allows DynamoDB to quickly find all data for a given user. The sort key, event_timestamp, allows us to efficiently query a user's events in chronological order. This design is optimized for the application's access pattern: get all recent events for this one user. Follow-up questions. Follow-up question 1. Why not just store everything in a powerful Redshift cluster and use it for both OLTP and OLAP? Answer: because they are optimized for different access patterns at a fundamental level. Redshift is a columnar database. It is incredibly fast at reading a few columns from millions of rows, OLAP, but it is very inefficient at writing or updating a single row, OLTP. DynamoDB is purpose-built for massive concurrency and low-latency point reads or writes, OLTP. Using one for the other's job results in poor performance, high costs, and a system that excels at neither. Follow-up question 2. What is the difference between a star schema and a snowflake schema in Redshift? Answer: a star schema has a central fact table connected directly to several denormalized dimension tables. It is simple and results in fewer joins, which is often faster. A snowflake schema normalizes the dimension tables further. For example, a dim_users table might link to a separate dim_geography table. This reduces data redundancy but requires more join-s, which can make queries more complex and sometimes slower. For most data warehouses, a star schema is the preferred starting point. Follow-up question 3. Curveball: a user in your dim_users table moves from one country to another. How do you update their record without losing the historical fact that their past events originated from the old country? Answer: this is the classic slowly changing dimension, SCD, problem, solved with a type 2 SCD. Instead of update, the user's country in place, we would, 1. Mark the existing record as inactive by setting an is_active flag to false and populating a valid underscore to timestamp. 2. Insert a new record for the same user_ID with the new country, setting is_active to true and valid underscore from to the current date. This creates a new version of the dimension record, preserving the full history and ensuring historical queries remain accurate. How to ace this whiteboard challenge? How to explain it? Immediately identify the OLTP versus OLAP conflict as the core of the problem. Propose a hybrid architecture with DynamoDB and Redshift as the solution. Whiteboard the architecture first. Then, write the specific data models, a star schema for Redshift and a key-value model for DynamoDB. Why it impresses: a good answer designs a star schema. A gold standard answer designs the entire hybrid system, correctly mapping DynamoDB to OLTP and Redshift to OLAP, and can confidently discuss advanced warehousing topics like Snowflake schemas and Type 2 SCDs. This demonstrates true architectural thinking. AWS well-architected connection. This design is a masterclass in the performance efficiency pillar. It is about selecting the right tool for the job to achieve maximum performance for two opposing workloads. It also touches on cost optimization by not over-provisioning a single, compromised database. Here's a challenge for you to practice and take your skills to the next level for interviews. Using the architecture above, design the data models for an e-commerce system with orders and products. You will need a fact_orders table and at least two dimension tables, dim_products and dim_customers. What columns would you include in each? How would you handle a change in a product's price over time, a Type 2 SCD problem?
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or both to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, DynamoDB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle.
Whiteboard Challenge 19, AWS Data Pipeline Design, IoT Ingestion to S3 to Data Lake to Analytics. Question: what is this challenge and why does it matter? Answer: design a resilient, scalable pipeline that ingests high-velocity IoT telemetry, lands raw data in S3, a data lake, prepares curated analytics-ready tables, and exposes those tables for ad hoc and production analytics. Interviewers want to see service trade-offs, Kinesis versus Kafka versus IoT Core, efficient file formats or partitioning, metadata or catalog strategies, glue or lake formation, and how you support both batch and near real-time analytics while keeping security and cost under control. The challenge and time box. You have 20 minutes. Propose an end-to-end design, device authentication to ingestion to raw landing, S3, cataloging to transformation to analytics. Explain partitioning strategies, data formats, schema evolution handling, near real-time versus batch trade-offs, security, encryption and least privilege, and monitoring or observability. Gold standard architecture, IoT to S3 data lake to curated zone to analytics. 1. IoT devices, edge sensors or mobile, authenticate and publish telemetry. 2. AWS IoT Core/MQTT broker to validates device identity, applies basic routing and rules. 3. Kinesis data streams or Kinesis data firehose to streams high-throughput telemetry, firehose for simple delivery, data streams for custom processing. 4. S3, raw or landing, immutable, append-only objects, JSON or ND-JSON, with lifecycle rules. 5. Glue catalog plus lake formation to central metadata or catalog and fine-grained access control. 6. ETL/streaming transform, glue spark/glue streaming/KDA/Flink, convert raw JSON to Parquet or ORC, partition by date/device_type/region, enrich with lookups. 7. S3, curated/partitioned, analytics-ready Parquet or columnar files. 8. Query and analytics to Athena or Redshift Spectrum for ad hoc queries, Redshift or EMR for heavier BI, optional timestream for time series fast queries or a materialized OLAP layer for dashboards. 9. Near real-time path to Kinesis data analytics or Lambda plus DynamoDB/timestream for sub-second metrics and alerting. 10. Observability to Cloud Watch metrics, Kinesis or DLQ, Glue job logs, S3 access logging, and Athena query logging. Architecting an AWS IoT data platform. Picture millions of devices pumping telemetry. IoT Core authenticates devices and pushes events into a streaming tier. We land immutable raw data in S3, our single source of truth. An automated ETL layer using Glue or Flink converts raw JSON into partitioned Parquet. From there, analysts query the data via Athena or Redshift Spectrum. For sub-second needs, we fork a real-time path into a service like timestream. This design cleanly separates concerns, durable landing, scalable transformation, and flexible analytics. Here is the implementation artifacts, producer, ETL, and DDL, using Python implementation I would use. Disclaimer, always test code in a non-production environment. The producer, device, sends a JSON payload to a Kinesis data firehose stream. Firehose is chosen for its simplicity in delivering data directly to S3 with built-in buffering, compression, and format conversion. The Glue ETL job is the heart of the transformation. It reads raw data, derives a partition key, event_date, and writes the data out in the optimized Parquet format, partitioned by that key. This is critical for query performance and cost. This DDL, typically created by a Glue crawler, begins the definition of our queryable table. We define the columns, device_ID, TS, temp, and their data types that exist within our Parquet files. Next, we declare the table as partitioned by. This tells Athena that the data in S3 is organized into folders based on the event_date column, enabling partition pruning for faster, cheaper queries. The stored AS Parquet clause specifies that the underlying data uses the efficient, columnar Parquet format. This allows for columnar pruning, further reducing the amount of data scanned. Finally, the location clause points the table metadata in the Glue catalog to the root S3 path where the partitioned Parquet files are stored. Follow-up questions. Follow-up question 1. Kinesis data streams versus Kinesis firehose versus managed Kafka, MSK, how do you choose? Answer: Kinesis Firehose is the simplest choice for streaming data directly to a single destination like S3, with minimal code. Kinesis Data Streams is more flexible. You use it when you need multiple, independent real-time consumers, for example, one for S3, one for alerting. Managed Kafka, MSK, is for teams that are already invested in the Kafka ecosystem or need features like long-term data retention in the stream itself. For this IoT to S3 pipeline, Firehose is the most operationally efficient choice. Follow-up question 2. How do you handle schema evolution if the IoT devices start sending new sensor readings? Answer: This requires a robust strategy. The raw S3 bucket should always accept the data as is, schema on read. The glue crawler will detect the new fields and update the raw table schema. In our glue ETL job, we would then explicitly map these new fields, apply any necessary transformations, and add them as nullable columns to our curated Parquet table. For proactive governance, we would use the AWS Glue schema registry to enforce compatibility rules, for example, allowing new fields but not deleting old ones. Follow-up question 3. Curveball: How do you ensure data quality and handle bad messages from faulty devices? Answer: You build a validation and dead lettering mechanism early in the pipeline. I would change the initial ingestion path to IoT Core to Kinesis data streams to Lambda. The Lambda's first job is to validate the incoming message against a schema. If it is valid, it passes the data to Kinesis Firehose for delivery. If it is invalid, the Lambda routes the malformed payload to a dead letter queue, DLQ, which is an SQSQ or another S3 prefix, for later inspection. This prevents a single faulty device from poisoning the entire data lake. How to ace this whiteboard challenge? How to explain it: Structure your answer around the key data lifecycle stages: ingest, store, process, and analyze. For each stage, name your primary AWS service and justify your choice against alternatives. A diagram is essential. Why it impresses: A good answer lists the services. A gold standard answer can articulate the trade-offs: Firehose versus streams, design for operational realities, schema evolution, bad data, and propose a dual path, batch plus real-time, architecture. This demonstrates true architectural fluency. AWS well-architected connection. This design heavily emphasizes the operational excellence and cost optimization pillars by prioritizing serverless and managed services, IoT Core, Kinesis, Glue, Athena. This minimizes infrastructure management and aligns costs directly with usage. Here's a challenge for you to practice and take your skills to the next level for interviews. Add an enrichment step to the Glue ETL job. The job should take the incoming device _ID, perform a lookup against a device metadata table in DynamoDB, for example, to get the customer _ID and firmware version for that device, and add this information to the curated Parquet records. How would you perform this join efficiently in Spark? Challenge 20, Netflix-like data platform, AWS plus Python. Level 4 has pushed us through streaming, IAM security, and hybrid schema design. But now, it's time for the ultimate whiteboard test, the kind of question reserved for principal engineers and system architects. Imagine you're asked to design a Netflix-like data platform, one that can handle millions of concurrent streams, ingest every click and playback event, store it reliably, and use it to deliver real-time recommendations. This isn't just a pipeline, this is the architecture behind experiences. Welcome to Challenge 20, the capstone of our series. Whiteboard Challenge 20, Designing a Netflix-scale end-to-end data platform. Question: What is this challenge and why does it matter? Answer: This is the capstone challenge, designing a full-scale data platform for a service like Netflix. It's not just one pipeline, but an entire ecosystem, millions of users generating events, data flowing into a lake, analytics driving business insights, and machine learning models powering recommendations. This tests your ability to think as a system architect, balancing streaming, batch, security, governance, and ML integration. Acing this sets you apart as a next-level data engineer capable of designing business-critical platforms. The challenge and time box. You have 25 to 30 minutes. Design an end-to-end data platform for a Netflix-like service. Your platform must 1. Ingest events in real time, 2. Store raw data durably, 3. Curate analytics-ready datasets, 4. Support BI queries at scale, 5. Feed ML pipelines for personalization, and 6. Power real-time dashboards. You must justify your architectural choices and explain how the platform would evolve. Gold Standard Architecture, Part 1, The Data Foundation. The architecture begins by building a robust, scalable foundation for all downstream analytics and machine learning. 1. Real-time event ingestion. A user's action, for example, watching a video, generates an event. The application sends this event to an Amazon Kinesis data stream, which acts as a scalable front door for all user behavior data. 2. Data lake formation. Kinesis data firehose consumes from the stream, batches the events, converts them to Parquet, and writes them to our S3 data lake in a raw zone. This becomes our immutable source of truth. 3. Feature engineering at scale. A daily AWS Glue Spark job reads the raw events. It joins this data with content metadata, for example, genres, actors, to compute powerful ML features, for example, user_genre_affinity, watch_duration_percentage. 4. Centralized feature store. The Glue job writes these computed features into Amazon SageMaker feature store. This provides two tiers, an offline store, in S3, for model training and an online store, low latency, for real-time inference. Gold Standard Architecture, Part 2, Analytics and ML Serving. With the data foundation in place, we can now power the consumption layers that deliver business value and create a virtuous feedback loop. 5. Model training and deployment. An Amazon SageMaker training job reads from the offline feature store, trains a recommendation model, and deploys it to a real-time, auto-scaling SageMaker endpoint. 6. Serving real-time recommendations. The application calls the SageMaker endpoint with a user_ID. The endpoint retrieves the user's latest features from the low-latency online feature store and returns a personalized list of recommendations. 7. Analytics and feedback loop. Business analysts use Amazon Athena and Amazon Redshift to query the curated data lake and measure the engine's performance. When a user clicks a recommendation, that new event flows back into Kinesis at the beginning, creating a virtuous feedback loop that constantly improves the system. In this final challenge, we'll go beyond the basics and walk through how an MVP evolves into a fully fledged Netflix-like data platform. We'll start small, scale carefully, and finally reveal the end-to-end architecture that brings everything together. MVP stage, minimal build. We start small with an MVP, just Kinesis to S3 to prove the data flows. This is where we validate the core idea. APIs feed events into Kinesis, which land directly in S3 as the raw source of truth. Using Athena, analysts can run ad hoc queries. It's fast to deliver and proves that the pipeline works. Growth stage, scaling analytics. As we grow, we add Glue and Redshift to power deeper insights and faster queries. As the platform grows, we introduce DynamoDB for quick session lookups, Glue ETL jobs to curate and transform data into Parquet, and store it in S3 with a proper data catalog. Redshift and Athena open the door for richer BI dashboards and scalable analytics. Scale stage, enterprise ready. At scale, the architecture becomes Netflix-like, AI-powered recommendations, real-time dashboards, and global content delivery. In the scale stage, we combine real-time and batch seamlessly. We enrich data streams with ML models, use Kinesis analytics for sub-second insights, and leverage TimeStream or DynamoDB for operational dashboards. On the batch side, S3 serves as the data lake powering Redshift, Spark, and machine learning pipelines. This is where we handle Netflix-scale workloads. Full architecture, final Netflix-like platform. Here's how a modern Netflix-style data platform comes together, from clicks to recommendations. On the left, the ingestion layer starts with raw user interactions: every click, play, pause, search, and rating. These events flow in real time into the platform. Next, the storage layer collects this firehose of data into a data processing zone. Think of it as the raw landing zone where nothing is lost, the single source of truth for downstream use cases. The processing layer comes in two flavors. On one path, data flows into analytics pipelines that power dashboards, BI tools, and A or B testing. This feeds into governance, where data quality, lineage, and compliance rules are enforced to keep the ecosystem trustworthy. On the other path, raw data feeds into a feature store. This is the beating heart of machine learning: standardized, reusable signals like minutes watched last week or preferred genres. These features fuel model training, where personalization and recommendation models are continuously refined. Notice the separation of concerns. Ingestion ensures nothing is missed, storage provides durability, processing enables both BI and AI, and governance ensures the entire ecosystem remains secure and reliable. This architecture is the blueprint behind every personalized carousel and trending now section, balancing operational scale with analytical depth, the essence of a Netflix-like system. Here is the implementation artifact: the core batch ETL job, PySpark. Using Python implementation I would use. Disclaimer: always test code in a non-production environment. We start by creating a Spark session. In a production AWS environment, this code would run as an AWS Glue job or on an EMR cluster. We explicitly define a schema for our incoming data. This is a best practice that improves performance and reliability over schema inference. The job reads raw JSON telemetry events from the S3 raw zone. Spark reads this data in a distributed fashion. We add a derived column, event_date, from the event timestamp. This will serve as our primary partition key for the curated data, which is critical for query optimization. Finally, we write the transformed data frame to our curated zone. We use the efficient PAR-K format and partition the data by event_date. This layout is highly optimized for analytical queries with Athena and Redshift Spectrum. Follow-up questions. Follow-up question 1. How would you evolve this platform from an MVP for a new startup to a global scale service? Answer: you would evolve it in phases. MVP, focus on the core batch path, Kinesis to S3 to Glue to Athena. This delivers business value quickly with minimal operational overhead. Growth phase, add Amazon Redshift for performant BI and introduce the SageMaker feature store and training pipelines to launch the first version of the recommendation engine. Global scale, architect for multi-region. This involves replicating S3 data, deploying SageMaker endpoints in multiple regions close to users, and potentially using a globally distributed database like Aurora Global Database for metadata. Follow-up question 2. How do you handle data governance and security in a platform this complex? Answer: governance is critical. I would use AWS Lake Formation to manage permissions on the Glue data catalog and the underlying S3 data. This provides fine-grained, column-level access control. All data at rest would be encrypted using customer-managed KMS keys, and access would be strictly controlled by least privilege IAM roles. All API access and data access would be logged with CloudTrail for a complete audit trail. Follow-up question 3. Curveball: the business wants to personalize the user's homepage in real time, based on what they just watched in the last 30 seconds. How does your architecture support this? Answer: this requires activating the real-time path. The batch features are too slow. The architecture would be: 1. Kinesis Data Analytics, Flink, would read the raw event stream. 2. It would perform a stateful calculation, for example, users' last 5 watched genres, over a short, sliding window. 3. It would write these near real-time features directly into the SageMaker online feature store. 4. When the application requests a recommendation, the SageMaker endpoint can now retrieve these ultra-fresh features and generate a recommendation that reflects the user's immediate context. This is how you achieve true real-time personalization. How to ace this whiteboard challenge. How to explain it: tell the story in phases, MVP to growth to scale, and by data path, batch versus real-time. Use a diagram to anchor the conversation. Show how each component serves a specific business need. Why it impresses: this answer goes beyond a single pipeline to show an integrated platform. It addresses the full lifecycle, including ML, real-time analytics, and non-functional requirements like governance and multi-region deployment. It proves you can think like a data platform architect. AWS well-architected connection: this design is a masterclass in the framework. It is reliable, decoupled services, multi-region, secure, KMS, IAM, lake formation, performance efficient, separate paths for batch and real-time, and cost-optimized, tiered storage, serverless components. Here's a challenge for you to practice and take your skills to the next level for interviews. Design the data model and update logic for the SageMaker feature store. Define two feature groups, one for batch-updated user profile features, for example, primary_genre_preference, and another for stream-updated session features, for example, current_session_watch_count. Explain how the glue job and the kinesis analytics job would write to these two different feature groups. We've climbed rung by rung: warm-ups, data transformations, big data optimization, and expert system design. Now, the final rung glows, level 4's apex. The role of the data engineer evolves into platform architect. This is the test that ties everything together: streaming, security, modeling, governance, and machine learning, in one unified system. Congratulations! You've completed the top 20 AWS plus Python data engineering whiteboard challenges. If you've followed along, you've not only learned how to solve interview puzzles, you've learned how to think like a data platform architect. From humble string manipulations to designing a Netflix-scale data lake, you've proven one thing: data engineering isn't just about moving data, it's about shaping the systems that shape the world.
Hi, friends. Imagine walking into any AWS Python Data Engineer interview with the answers that exactly what your interviewer wants to hear, because each response is meticulously aligned to the AWS well-architected framework and proven real-world use cases. Imagine this: you're not just recalling facts. You're explaining complex integrations with clarity, justifying design choices with AWS best practices, and confidently handling unexpected technical challenges. That's the power this bundle gives you. Trust me, by having this bundle in your kitty, you people will be always one step ahead of your interviewer with the kind of depth this question and answers has. It's comprehensive, practical, strategically designed, and built to instill genuine confidence. Every answer is a deep dive, aligned with AWS best practices and real-world use cases to boost your credibility. You'll get practical Python or PySpark or bow to 3 code snippets, master challenging curveball questions, and learn to stay ahead of the interviewer with our unique follow-up probes and enhancement tips. This very comprehensive and a dream bundle of 35 PDFs contains 1,750 plus interview questions and answers of AWS services related to data engineering like Amazon Redshift, AWS Glue, Amazon S3, Amazon RDS, Amazon DynamoDB, AWS Lake Formation, Amazon Athena, Amazon EventBridge, etc., for AWS Python Data Engineer interviews. Each PDF, encompassing 50 question and answers for a specific AWS service, for example, Dynamo, DB, Kinesis, S3, is meticulously crafted to mirror the complexities and demands of real-world AWS Python Data Engineer interviews, ensuring candidates are well prepared for both technical and practical challenges. These question and answers are structured to reflect the multifaceted nature of data engineering roles, where professionals must design, optimize, secure, and troubleshoot scalable data pipelines in production environments. By incorporating a diverse range of question types like curveball questions, cross-service integration questions, automation and operational efficiency questions, performance and cost optimization questions, security and compliance questions, etc., each PDF simulates the high-stakes, dynamic scenarios that interviewers use to evaluate a candidate's technical depth, problem-solving skills, and ability to apply AWS best practices in real-world contexts. Why do you people feel like conquering your interviews with great confidence? Because we don't just give you answers. We teach you to think like a seasoned and comprehensively prepared data engineer. By aligning every solution with AWS best practices and real-world scenarios, preparing you for curveballs and helping you anticipate follow-up questions. Please check description or comment section of this video for a downloadable link of this dream bundle. I have provided previews of 10 to 15 questions for every PDF. So, you people can check previews before downloading this awesome dream bundle. For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers, for 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.